first direct detection of gravitational waves, the remarkable event of GW 150914, observed on 14 September 2015. This detection confirmed a century-old prediction of Einstein's general relativity and marked the dawn of gravitational wave astronomy. In the decades since, GW observations have evolved into a precision science, providing insights into compact binary population, neutron star physics, stellar evolution, cosmology, and test of gravity in strong field regimes. The first detection not only validated decades of theoretical and experimental efforts, but also set the stage for an era in which gravitational waves are central to multi-messenger astrophysics. Our event today reflects both this history and the exciting prospects ahead. We will have 3 talks by our distinguished speakers, followed by a panel discussions, where our panelists will share their perspective on the progress so far and the challenges and opportunities that lie ahead in gravitational wave science. We begin with our first talk today. It's my privilege to introduce our first speaker, Professor G Arun. He is a faculty at Chennai Mathematical Institute since 2010. He completed his PhD at Raman Research Institute in Bangalore under the guidance of Professor Bala Iyer, followed by postdoctoral research at Institute of Astrophysics in Paris and Washington University, St. Louis. His research spanned several key areas of gravitational wave physics, from modeling compact binaries to developing waveforms, templates that are widely used in GW data analysis, from testing Einstein's theory of general relativity to exploring the connection between short gamma ray bursts and compact binary mergers, and so much more. For his pioneering work, he has received the prestigious Swarn Jayanti Fellowship for Young Scientists, and he was also awarded the Special Breakthrough Prize along with other LIGO scientific collaboration members for the discovery of gravitational waves. He now serves as a co-principal investigator of LIGO India scientific collaboration, helping lead one of India's most ambitious scientific ventures. Please join me in welcoming Professor G Arun.
I hope this is okay. It's mostly for YouTube audience, I think. Okay, I hope you can hear me okay, and thank you so much for having me and Chandra and others for organizing this wonderful event, which of course, as Nithi mentioned, is about the 10th anniversary of the first detection, which really changed the way we look at astronomy. So in this talk, I'm going to kind of talk to you about the broader landscape of gravitational wave astronomy, and where we were historically and where we are currently, and where we are headed in the years to come. And this will be, I will give you an overview of the entire field, which will be followed by detailed things by Ajit Mehta, Sriram, and evening panel discussion by Manjari Bakchi and others. So let me get started with things. So my talk is going to talk about what is so special about gravitational waves. Why are we so excited that we are celebrating its 10th anniversary? So how do we detect gravitational waves, and where do we stand, and what are the future prospects? Please feel free to stop me in between, because then I'll get an idea about how closely you are following. Okay, so this is a picture of the universe in some sense, starting from the center is at the solar system. As you go out, we have stars, we have galaxies, we have clusters of galaxies, and so on and so forth. In all these subjects host really interesting astrophysical events, which we need to probe, or we need to understand, and which we have been doing so far. So how do we probe? How do we probe the universe? There are various cosmic messengers. One thing can be particles such as cosmic ray particles, neutrinos, and so on, which we can see only up to very nearby distances. But the most dominant thing that we have used to probe the universe is really light. Light in various bands of the electromagnetic spectrum we have been using to follow events which happens in various locations in the universe, which have been very successful. And most of our understanding of the universe until 10 years back came from using lights in various form. The last one, which is what is going to be the topic of this talk, is gravitational waves and why it changed or why it complements the existing ways of probing the universe using astronomical techniques. Okay, so as I mentioned about light, as you know that you are familiar with lights in various bands of the electromagnetic spectrum, starting from radio to the gamma ray, and these are showing you some of the electromagnetic telescopes, some of them on the ground and some of them in the space, which we have been using to follow transients and maybe something long-lasting phenomena and so on. And we gather, as I mentioned, that various entities like galaxies, galaxy clusters, and all these things host various phenomena, which we track or which we detect up to whatever distances we can with these electromagnetic telescopes, and that is why how we have learned most of the things that we know about the universe. Right. What I'm going to talk about is that what about phenomena which doesn't emit light? For example, if there are phenomena which are gravitationally active but doesn't emit light, such as black holes, for instance, how do we understand that dark side of the universe which doesn't emit anything in light? This is where exactly the gravitational waves come into picture, where we can use, even in the absence of electromagnetic waves, we can use gravitational waves as a way of probing this dark phenomenon, dark in the sense which doesn't emit light. And it's a new kind of cosmic messenger, in the sense that just like neutrinos and lights and so on, we can use it to probe the universe. Right? Yeah. On this for the camera thing. Okay. Okay, so what are gravitational waves? In a nutshell, this is Einstein's prediction of general theory of relativity, which was made in 1916. So Einstein argued that Einstein's picture is about space-time. So this is showing you okay, 1 second. So this is showing you that if you have dynamical masses, that means masses which are accelerating in the space-time, because gravity is space-time, and any dynamical changes to space-time will cause ripples in the curvature of space-time. That is intuitively what gravitational waves are. I'm showing you two objects going around each other, and that emits gravitational waves which are sending out as ripples in the curvature of space-time. So they are generated just like electromagnetic waves. They are generated by accelerating masses as opposed to accelerating charges that produce electromagnetic waves. And in the space-time picture, you can think of them to be producing ripples in the curvature of space-time, which kind of propagate out from the source. According to Einstein's theory, they are transverse, which means that the waves make changes only along transverse direction of propagation and travels at the speed of light. So this is strictly to Einstein's theory. You may have another theory of gravity where these are not followed, but we are for now closely following Einstein. And another important thing is there are, at the leading order, they are quadrupolar in nature. So if you remember, electromagnetic waves are dipolar at the leading order, whereas the Einstein's theory, gravitational waves are quadrupolar and have two states of polarization, similar to Ex and Ey that we think of electromagnetically. There are two states of polarization. So there are many features that electromagnetic waves and gravitational waves share, such as two polarization, speed of light propagation, etc. But there are many distinguishing features, especially the fact that one is produced by accelerating or dynamical masses, other one is from due to charges and so on. So we'll see them, and of course the underlying theory of them are quite different. One is described by Maxwell's equation, and this is described by Einstein's theory, which is highly nonlinear as opposed to the Maxwell's theory. Okay, so this is a summary of what gravitational waves are in the nutshell. Now let's look into the two states of polarization that I mentioned. Right? So this is, we refer to this as two as cross and plus, as you can see that. So what I'm now talking about is, suppose you have a ring of particle originally in the form of a circle, so small kind of test particle, and you have a wave passing orthogonal to the plane of the screen. According to Einstein's theory, this passing wave is going to set this ring of particle into motion. That would mean that it will be, you can see that there are two modes. One is stretching and squeezing in one direction, one along like a plus kind of sign, and this one is like a cross one. So these are the two state of polarization. Regardless of what they do, so the important thing to keep in mind is that if you have a ring of particle, they are going to be differential motion between them, in the sense, on the one sense it will be compressed, at the same time on the other direction it is going to be expanding or kind of elongated. So this is an important feature that we will make use of when we try to detect gravitational waves, but it's just to give you an idea about how the two states of polarization look like. Okay, so stop me at any point if you have any questions. Okay, so now let's look into a gravitational wave that is going by. So I'm showing you a waveform like a sinusoidal wave, but you should keep in mind the wave is traveling transverse to the plane, and so you start off with a ring of particle in a circular thing. As you go, it becomes ellipse, then it becomes circle again, then it becomes ellipse in the other direction, then again it goes back to circle, right? So this is the kind of, as the wave goes by, this is how the ring of particle is going to be deformed. Now, how do you measure the strength of the wave? You would intuitively imagine that the separation, so what this is doing is to change change the distance between two particles to change. Suppose if we take these two particles and a wave is going by, and the original length was L, suppose, and now a passing wave is going to change the distance because it has become kind of smaller. I can define a dimensionless parameter delta L by L, which is the fractional change in the change in the separation compared to the original separation, and this is what we normally call as gravitational wave strain. Okay. So you can imagine that a stronger wave is going by, you would expect that delta L is going to change for the same ring of particle, and H gives you a direct measure of how strong the passing gravitational wave is. Okay. So this is useful concept. So you can imagine that for a kind of, okay, I think I'll come back to that later. So now this is about the strength of the wave. Now if you want to think of a source that is generating a wave, if you write down the gravitational waveform in Einstein's theory, you would see that there are two dependencies. One is, of course, it depends upon mass, which is kind of understandable. You expect gravity to be higher when the mass is high, and it goes inversely with distance, which is simply telling you that when it's far away, it is weaker, and when it's nearby, it's kind of stronger. That's the first kind of dependence. Second dependence is more important. It is telling you that a gravitational wave is stronger when you have the m by r ratio. So r is like a size of the object, and mass, m is the mass. So when it's called compactness, because it is telling you that how compactly or how you are packing the existing mass. If it is extremely compactly packed, that means m by r is very high. For a given m, your r is very small, size is very small. So when the compactness, I would say, is high, you expect the sources with high compactness to generate waves which are very high, kind of high strain. Okay. So this is important to keep in mind, that apart from the mass being high, which is intuitive, you also want the mass to be packed compactly, and you have to really, yeah. In some sense, if you want to think of density, I'm thinking about only F. So density will be m by r cube. So it is related to density. The way it appears in the waveform is only as m by r. That's why I'm compactness. But it's dense. Kind of very dense objects will be more compact, as you can imagine, intuitively. Okay, so this is how the gravitational waveform would look like, and this is good to know. So we have seen how the passing gravitational waves affect a ring of particle, and we have seen how the source should be if you want to have very high or a strong gravitational wave signal. So that means that when you can't, if you want with the kind of technology we have, if you want very strong gravitational waves, you have to look up to the sky and look into very compact stars that are in the sky. Two of them are, one of them is a neutron star, which is roughly speaking one solar mass is packed into 10 kilometers approximately, and it's a star very rich in neutrons. Dominantly it's going to be neutrons. So they are believed to be end products of stars. When stars undergo an end state of stars, you can be supernova explosion, which can give you a neutron star. Similarly, if the mass of the star that undergoes supernova explosion is even more, you can get a black hole where the entire mass of the star collapses to a single point, which we call a singularity, and you have some horizon, etc. So there is no matter inside. It's so the entire matter has fallen to a kind of single point, and it's such a strong gravitational field that from inside the black hole nothing can escape. Okay, so these are like extremely compact objects that we can think of in the astrophysical context, and any binary systems, that means two objects going around each other, consisting of two black holes, one neutron star and a black hole, or two neutron stars, are likely very strong source of gravitational wave. I mean, this is as strong a gravitational waves we can get from the astrophysical context. So we have to see that what kind of technology we need to develop to detect these things. These are as strong of waves you can get in the astrophysical context. Okay, so we are now going to look into or kind of restrict to binary black holes, binary neutron stars, and neutron star black hole binaries as possible sources of gravitational waves. Yeah. It can create. Suppose you have a neutron star or black hole that is accreting, for example. So what you need is that the space-time around the black hole should be dynamical, right? So suppose you take a neutron star and it's accreting, meaning from somewhere else it is matter is falling in. Of course, it will be, it is going to create ripples, but you can imagine that compared to two black holes coming closer to each other, the strength of the signal will be weak. Right, so accreting neutron stars are very good source, and but we can detect them only in our nearby universe. Compared to two black holes merging, which are very strong, two of the black holes are there, which we can go up to large distances. So accreting neutron stars and black holes are something which we know in our galactic system may be existing, but our sensitivity currently is not high enough to reach kind of thing. But eventually, one day in the next few years, as we improve sensitivity, we hope to see this class of sources also. Yeah, I mean, I think I'm just focusing on what we detected so far. There are many sources which we are yet to detect. I'm not going to talk about them. That's why it's restricted to binaries. Okay. Okay. So now just coming back to the strain argument again. Suppose you think of something which we can generate on in a lab. For example, suppose you have two 1 tons dumbbell with 2 meter separation going around each other, with 1000 hertz kind of frequency. That's extremely rapid as we can do in the lab. If you compute your h, that is going to be 10 raised to minus 39. Right? That's extremely tiny. That means that if you separate two test particles with 1 kilometer away, the delta L, that the L into this, is going to be 10 raised to minus 36 meter. So the kind of delta L that it will impart on two particles separated by 1 kilometer is 10 raised to minus 36 meter, which is extremely tiny. If you go to the astrophysical context, two binary black holes at 100 megaparsec, which should be reasonably abundant, you get your delta L, the equivalent thing here, to be 10 raised to minus 18 meter. Now, 10 raised to minus 18 meter, of course, is 1 by 1000 of the size of atomic nucleus, but even then it is much better. It's 19 orders of magnitude better than what we can do on Earth. Right? So this is much, though this is indeed a challenge, but this is a challenge which one can try to attempt compared to this one, which may take 100 years. So this is what you would require to really use it as a kind of communication or whatever, which will take some more time. But right now we are here where our technology has grown to detect sub-nuclear displacements due to astrophysical gravitational waves. Okay, so now let's look into different ingredients that go into the thing. I'm going to show you how the binary black hole, what is a binary black hole and how does it give you gravitational waves. So as I mentioned, these are two black holes which are orbiting around each other, and because according to Einstein's theory they emit gravitational waves, the emitted energy has to be taken away from something, that is from the orbital energy. Because of the emission they come closer. Once they come closer, you know the gravity is stronger, so this emits even stronger, and so this is like a runaway process which will bring them kind of close to each other. Eventually these two black holes will come and merge due to the emission of gravitational waves, and that is what we hope to see. I'm going to show you what is called a numerical relativity simulation, which is like solving Einstein's equation on a supercomputer kind of in its full generality, and this is showing you so these are two black holes, and what is shown here is the waveform. So you can see that initially they are all sinusoidal type of wave, very slowly in spiraling, but as this process goes on, as I mentioned, it's a runaway process. As it goes on, you'll see that the waveform, both the frequency and the amplitude of the waveform increases, as you will see. So the red one on the what is shown here is can talk about the strength of the gravitational field as they come closer. It's a bit more a complicated construction that don't worry about it so much. But this is, as you can see, when they come closer, they go kind of faster, which means it's high frequency, and emission is stronger because they're closer, and this will go. So I think you can see that this is now going extremely high. They merge, and then then the last thing is called a ring down, which is yeah, that's all. So then a new black hole is formed by the merger of two black holes in this case, and they give you gravitational wave, which is like a long in spiral, followed by a merger, that is a peak, and a ring down, rapid ring down, where you saw this to be exponentially damping. So this class of sources, so now I mean it's also clear that using Einstein's theory, we can compute gravitational waveforms for different kind of sources. So we know how the waveform model is, and we can construct copies of waveform for various parameters, masses, and so on, which is actually advantage to us, which I'll tell you how we make use of it. Now in terms of detectors, I mentioned about delta L being kind of subnuclear displacement. We have different types of detectors on Earth. So these are two LIGO detectors in the US. This is a Virgo detector in Europe. GEO is a small prototype. So these are 4 kilometer, this is 3 kilometer, and Kagra is also 4 kilometers in Japan. Right? These are the four interferometers that are operational, and we are hoping to build LIGO India in the next 5 years or so. So this is what, this is a worldwide network of gravitational detectors which are capable of, which will be, or some are and some will be capable of detecting gravitational waves of the type I mentioned. So you can see this one of the LIGO detector. This got two end stations with 4 kilometer away and a central thing, and this is so this is like the, I told you, ring of particle, and you're looking into the x and y axis of the ring of particles. So I'll just show you what exactly it works. So this is the two mirror. These are two particles. As a wave is going by, you expect that one mirror will come closer, one will be extended. So if you, it's an interferometer, right? So you are looking into the interference pattern at the output. You can originally set it to be dark fringe because you can cancel the thing exactly by adjusting arm length. But the moment the gravitational wave goes by, it is going to change the length, and because of the change in the arm length, your output will not be dark fringe anymore. You will get some light at the output, which is really our kind of strain data in some sense, and I'll show you how exactly it works, and that's roughly how it works. I'm going to show you the animation. So this again, these are the two end mirrors and the beam splitter. Laser is coming from here. So this is a laser light which gets split. It comes back. It is detected at the this photodiode output. So when there's oscillation of the end mirrors due to a passing gravitational wave, you expect some light. So this is again wave picture. Wave gets split into two, and they get bounced back and interfere at the central station. So originally we lock the detector, in the sense we lock it such that it's dark fringe. So there is nothing at the photodiode. So we keep a photodiode at the output to kind of track. But once there is a change in the arm length, as you can see, that the interference will not be completely destructive. You get some light because of the interference, and that in some sense is the a signature of a gravitational wave. Okay. Now, of course, this is all good story, but the real challenge is that you can imagine that we are, yeah.
So is the same as Michelson detector?
Correct.
And is the same to measure the speed of light?
Yeah, this same type of experiment, I think it's the same. Yeah.
So my question is, how do you distinguish this is comes from electromagnetic wave or this comes from gravitational? How do you
No. So the Michelson's, Michelson interferometer is the general setup, right? You look into interference pattern, that's all. So speed of light measurement was like you send light and you know that's a different scale altogether. Here this is a laboratory scale. Laboratory meaning large laboratory scale, and this is specifically devised to detecting gravitational waves. Okay. So in the following sense, so this is exactly what we do. Now the question you are asking can be that how do you detect the signal in the middle of noise? There can be various noises which can be there. It can be the randomness of the laser light itself. It can be seismic vibrations due to either cars going by or even an aeroplane going by. Even thermal noise when you suspend things, there are many noises in the detector. So to answer your question, both are Michelson class of instruments or interferometer, but this one is dedicated to detecting gravitational waves. And the question to ask here would be that how do you isolate the signal that I mentioned about the photodiode, and how do you separate them out from possible sources of noise? Right? Because you see, Michelson interferometer we do for various things. We can do in the lab also. We have tabletop experiments. So very general class of experiments, and whatever we set it to use, I mean there is some objective for each one of them. This one is set to detect gravitational waves because exactly monitoring the differential changes to the N mirrors, which are here the two test particles. Okay. So as I mentioned, the signals are extremely weak, and you are looking at how do we detect the signals in presence of noise, right? So this is indeed a challenge. I mean, if you have a strong signal, that's fine, but you don't know how frequently you will get a strong signal. So you have to deal with thermal noise, photon shot noise, seismic noise, and various other sources, because it's a very complex instrument in general. So this is indeed a challenge. But here is when we make use of our understanding of the signal. So as I mentioned, that we can model the signals extremely well in Einstein's theory. So I'm showing you, this is the template that I'm talking about. So what you do is that you take the data, you overlap various copies of the signal on through that, and whenever the signal in the noise matches with the waveform that you are kind of overlapping, the correlating, you get, this is like a signal to noise ratio. That means how loud the signal is. You would expect that you get excess in the signal to noise ratio. I'm just kind of sliding, and you can see these are all backgrounds, so there is nothing in particular there. But the moment the signal there matches with exactly with the template that I am doing the cross correlation, you get a peak in the signal to noise ratio. So this peak, when it's above a certain threshold set by statistical understanding of the detector, then we claim it to be detection candidate, right? We need to make sure that it's not due to something else. So we do various tests to make sure that this excess is not due to some instrumental artifacts and so on. So that is the challenge, that how do you make sure that some excess in SNR is not from some instrumental origin, but really from the astrophysical gravitational wave. So this is something the challenge. But what I want to stress is that theoretical understanding and our ability to model these waveforms very well in Einstein's theory really helps in looking for these weak signals that are buried in the data. So this technique is called match filtering, where you kind of where you cross correlate the signal, the data with a bank of what is called gravitational waveform copies, and you ask kind of which kind of waveform gave you the best or the highest SNR that you have got. Okay, so that is about all parts. So I told about the LIGO experiment, I told you about the waveform development, I told you about the data analysis techniques, at least in the nutshell. So this is really the context where 1509-14 happened. So I'll show you the history at the end, but LIGO detectors have had a first generation LIGO detectors, initial LIGO. They operated till 2010. They were upgraded to advanced LIGO and initial LIGO of course did not detect anything, which was expected given the rate of events and so on, but they were upgraded to advanced LIGO in 2015, September 14, when they were about, they were upgrading and they were about to start officially the scientific quality run, is when this event happened. So as the name is named after the date of the event, and what is shown here is the signal that I am superimposing it on the reconstructed numerical relativity thing. So this is an NR signal, and I am showing you the reconstructed template which will have error bar as you can see. So what we saw was really the in spiral merger and ring down of two black holes which are orbiting around each other and kind of falling in, giving you the signal. And what is shown here is the time frequency map. So it is showing you how the frequency increases as a function of time, as you would expect, and it's showing the energy is what this yellow one is showing the energy. So this is called chirp signal because it just goes on like a chirping bird, if you want to say. So this is the first detection. So after all these upgrades of LIGO and so on, and with all the developments in the waveform, in terms of constructive waveforms, the first detection happened in 2015, September 14th, and this is the event. I think we are going to see more about it in Ajit Mehta's talk about the properties and what we have learned after that. But one important thing to keep in mind, at least the frequency of gravitational waves LIGO detects is in the hertz to kilohertz regime, which is more like a audio signal. I mean, more like an audible band. Actually, it's not audio signal, it's in the audible band in some sense, and it is kind of interestingly, in that sense, complementary to light. So one light is like seeing something, and this is like listening to the universe. In the sense, if you plug it with some basic filtering to a speaker, you can hear this, this sound, which I will not play. You may have seen it enough. I'm bored of playing that sound over the last 10 years. Okay, so this is just to tell you, this is the first signal we detected, and which is like which is basically two black holes with 35 solar mass and 30 solar mass merging to give you a 62 solar mass black hole and 3 solar mass. The difference between them is radiated away in the form of gravitational waves, and this happened at around 440, 450 megaparsec away from us. And this is indeed, the fact that 3 of these gentlemen got Nobel Prize. Rainer Weiss, who is no longer with us, who passed away last month, and Barry Barish and Kip Thorne got Nobel Prize for contributions to. Rainer Weiss was the person who devised LIGO and who really constructed LIGO in some sense. Barry Barish was the man who is in control of the LIGO scientific collaboration, and Kip Thorne contributed to various theoretical development, which again played a very important role in the detection of the gravitational waves. Right? So with this, this kind of inaugurates a new branch of astronomy where we can, at least in principle, LIGO can detect gravitational waves from binary black holes and use it to probe the universe. So it's like a new branch of the new era in astronomy. Okay. So I still have half an hour to go. Okay. Okay, you can stop me more frequently if you want. So now I want to compare. There's like another event which happened, in early this year, 25/01/14, which means it's 2025, 14th January. As if it's a decadal tribute. So the signal is very similar to the binary black hole signal is very similar to what we saw on 2015, but you can see that because of the upgrades of over the last 9-10 years. So this is a signal that I'm showing you, and the noise is what is shown here, the kind of data that is there, and you can see that this is much smaller. The noise things are, we have controlled it much better, improving the sensitivity. And while this had an SNR of 27 or something, the first one, this had an SNR of around 80. This is signal to noise ratio, which means that how louder is the signal compared to the background noise, and this had an SNR of 80. And there are, it kind of gave you opportunity to do various things, and this most recent, this was released last week. You should take a look into this event. There are many outreach articles also about why this event is important and so on. But you can see, what I want to stress is a very similar event happened like a decade later, and we have improved our sensitivity significantly, as you can see from the noises on which I have superimposed the signal. Okay. Okay, so the next question you will ask is, okay, binary black holes is, at least we have detected one, and we detected many since then. How about binary neutron stars? So can we see, or have we seen binary neutron stars? And binary neutron stars have got a very interesting history, because they played a very important role in people realizing that gravitational waves are indeed physical. Because binary neutron stars can emit light. They emit typically in radio, and this is showing you the two, if there are two binary pulsars, two neutron stars, of which one could be a pulsar or both could be a pulsar. When they orbit around each other, you can track the light, the radio light from the source. And at least these two gentlemen, Hulse and Taylor, have observed this system in 1974, and they tracked. So if this system indeed emits gravitational waves, you expect that their period will decay. Right? So what they tracked is how the period of the system will decay over time. I'm showing you data till 2005, and they compared with the decay with the generalistic prediction. These are the red dots on top of it. So you can see that the decay of the orbital period of the binary pulsar follows exactly the predictions of G Arun. So the data until 1993 kind of established confidently that this is indeed, we are seeing the emission of, we are seeing indirect evidence for the emission of gravitational waves via decay of the orbit of this binary pulsar, and these two gentlemen were awarded the Nobel Prize in 1993. And of course, this did give a lot of boost to LIGO, because those who were skeptical about existence of gravitational waves and various things, they also got convinced that this should be real and one should be seeing them. But what we saw is, of course, a very early stage of this one. We are not seeing them merging. You can ask a question that these are like early stages. When they come closer, at least some of them will come closer, and they will merge. What will happen? So this is exactly what we would like to see, that when two, instead of saying in spiral, long in spirals of, early in spirals of two neutron stars, we want to see the merger of two neutron stars and what happens in those kind of stuff. I'm now going to show you kind of animation / simulation of what this. So you expect that compared to black holes, neutron stars got matter in it. You expect that matter can also give you light, right? So this phenomenon are known to be gamma ray burst. They were hypothesized to be, at least subclass of them were supposed to be coming from binary neutron star mergers, but there were no way of establishing it because we see only light, and there was no way of saying whether light is coming from is it really coming from binary neutron star. I'm going to show you a numerical animation of what happens when two neutron stars merge. These are two neutron stars, and they come closer and closer, then they merge. Okay, they merge. There is a lot of matter still around it, right? It gives you a jet-like thing along the. So typically they form a black hole. Black hole can accrete matter from this ejecta that is disrupted. It can give you a jet, and this gives you light. This jetted form of light is called a gamma ray burst, and it can give you various other forms of light as well, which I'm not going into. But you expect that you would also expect to see, if there's a binary neutron star merger, you would also see light associated with that. That's one of the thing you would see. You may not see light always for different reasons, because the light is will happen only on it's a jetted thing, right? So if you happen to be on the angle of the jet, you will see light, but gravitational waves you should see in any case. So we are asking whether we are seeing such events or we can see such events, or did we see such events with LIGO? Okay, and indeed we saw. This is 170817. This is 2017 August 17. We saw a binary neutron star merger. I am showing you the time frequency map of LIGO. This is how the merger. This is where the merger would end. And I am showing you the data from Fermi, which is a space-based gamma ray satellite. And like 2 seconds roughly after the end of the merger, the Fermi recorded a weak gamma ray burst, and this is called the GRB 170817A. And this was a very interesting event, because we were for the first time seeing two messengers, both light and gravitational waves. And it so turned out that this was a very close by event, 40 megaparsec, and this confirmed for the first time that the hypothesis that indeed two neutron star merger can give you a gamma ray burst. And this is, so when you use two messengers, it's called multi-messenger astronomy, where you can use both gravitational wave and the electromagnetic wave information to kind of understand the entire thing kind of a lot better. And we did learn a lot about gravitational waves. We learned a lot about the gamma ray burst and its jet from gravitational waves, but I'm not going to any of those details. So what I want to say is that unlike binary black hole mergers, which are relatively boring in quotes in terms of electromagnetic observations, binary neutron star mergers or neutron star black hole mergers can give you light as well, which makes the thing a lot more exciting. And this emitted light in various bands of the electromagnetic spectrum, starting from radio all the way up to the gamma ray, which are all detected, and it led to very rich science and astrophysics related to that. Right? So, but what we are not still seen is a neutron star black hole merger giving you light. We have seen neutron star black hole merger, but we are not seen light associated with that because of various things. Okay. So this is another important milestone in LIGO's thing, where we were seeing multi-messenger astronomy using both light and gravitational waves from the same source and try to reconstruct the phenomenon in a more coherent way from there. Okay, so I think, basically Ajit Mehta's talk will talk about what we have seen since then. I'm going to give a quick summary of what has happened since the first detection. Where do we stand with respect to them? So I'm showing you this is a number of events we have detected as a function of the observing run. So we have O1, that is when we detect the first one. O2 is when we detected the second binary neutron star, and O3, O4 and O4b, I think O4c plot, I wanted to replace the O4c plot. I think that plot is there in one of the screens or the poster outside. So you can see that as the sensitivity. So I'm showing you the sensitivity. It is telling you when the down it goes, the improved sensitivity, because really the noise you want to suppress, so you want to bring it down. You can see O1 is here and O4 is here. That is where we are taking data now. We are still taking data. So you can see that in various frequency bands there is considerable improvement in the sensitivity, which has come down, which is why you can see that this event which I compared 2025 and 2015, they were much improved because of the improved sensitivity. So as we improve sensitivity, we keep taking data, and we are at O4C, that's the third part of O4. And what we have seen, as you can see, is that this is 198 candidates, but it's 220 now, because candidates meaning they are what is detected in real-time analysis. So since 1 or 2 in the first observing run to 200, 220, we are seeing several of these binaries in various kind of diverse type of binary black holes, mostly binary black holes. And what we learn from that is something which Ajit Mehta's talk will be summarizing. So this is showing you the differences in so this is showing you a stellar graveyard pod, which means that it's these are dead stars at some level. So you can see that around 218 band is what I wrote. This is showing you the mergers. So this is saying this and this merge to give you this, etc. And the highest massive black hole is around kind of 200 odd that we have seen. And I think there are exceptional events which are there in the outside posters are there. They'll be telling you more in detail about what are the kind of classes of sources we have seen and why they are interesting, etc. There are graduate students around whom you can ask during the breaks. So this to tell you that there are different types. So you can one thing is to compare about the gravitational wave mergers, which are like here, compared to electromagnetic black holes. So these are black holes which are accreting, and because of the accretion of gas or particles, they emit light. And you can estimate mass from that. You can see that those kind of black holes are very small mass, but we are seeing masses up to 10 to 100 to 200 and so on. So there are significantly different kind of black holes that we are detecting in using gravitational waves. And and what kind of features and so on, I think you should take a look into the poster outside, and maybe Ajit's talk will summarize some of them for you in the afternoon talk. Okay, so just a quick summary is about we have now taken a census of compact binaries in the universe, and we have seen black holes with various masses and various properties we have studied. And also what I did not talk about is about it's a very good way to study, ask the question whether Einstein's theory is correct or not, because the signal that we detect are indeed Einstein's are consequence of Einstein's theory. We can ask whether detected signals are indeed Einstein's theory signatures, or there is some beyond Einstein effect. And so far there is no evidence for anything that is beyond Einstein, which could be due to our sensitivity. Maybe Ajit's talk also will mention about how we can use gravitational waves to measure the cosmic expansion rate, and how we can use it to understand the structure of neutron stars, and how we can search for new classes of sources like continuous. You were talking about about how if you are neutron star accreting, what kind of signal will that give, and whether we can detect and so on. There is there's a lot to be done, which in the years to come, and some of them we have done, which will be done with more accuracy in the forthcoming years. Then of course India wants to join the party. There's a LIGO India detector or LIGO Arun detector which is going to come up in Hingoli in Maharashtra, and this is we are going to start construction soon, and the hope is to complete by April 30, 2030. This is going to be a LIGO-like detector, like the two LIGO detectors, and is going to be kind of important because of the fact that this is going to give you a large baseline compared to LIGO detector. So which means that your sky coverage of the sources will improve, sky localization will improve, and more duty cycle in the sense of the detector performance. When you have multiple detectors, you can do new kind of GR test, and in terms of course, when sky localization is better, you can have much better synergy with other electromagnetic telescopes and so on. So it's going to be a very important development in addition to the worldwide network which I showed you earlier, which contains LIGO, Virgo, Kagra, and now LIGO India once it is operational. Okay, what about the future, right? In the future, there are plans for upgrades to LIGO in some sense, but a new detector as such, which will be 10 times more sensitive than what can be done. So when I say 10 times more sensitive, I mean to say that this plot, this will be factor of 10 better. So from here, kind of going down in 10, which would mean that because these are amplitude detectors, you can scan 1000 times more the volume, because R cube is the volume, and so that is what this will be. So this is called Einstein telescope. It's in Europe. It's a 10 kilometer arm length triangular kind of detector underground. They are yet to find this thing. And this is a US based detector proposed, which is called Cosmic Explorer. It's going to be 40 kilometer long arm length, 40. This is going to be, is still under active consideration. There is not funded yet officially. So with that, as we can see 1000 times we can go out. We can probe a volume that's 1000. Yeah. Yeah, I think they do. So they do take. So they'll be drilling through the kind of surface and kind of placing it. And Einstein telescope will be underground anyway. So I think they make sure that that's not affected. Okay, so typical time frame for them will be 2030 plus, 2035, and plus is plus. So hopefully it's not too much plus. But this is the kind of ground-based detector upgrade plan. Apart from that, you are going to have a millihertz detector in space, which would be by 2034. It's a ESA, it's a European Space Agency funded project called LISA, Laser Interferometric Space Antenna, which would be a triangular shaped antenna which will be going around the sun, trailing behind Earth's orbit. There are 3 satellites with 2.5 million kilometer arm length, and they will be, given the arm length, we'll be detecting them in the millihertz regime. And again, time frame is typically 2034. That is a well-planned space mission, funded, and they are kind of building various parts of it. So this should be out by 2034, which will of course, it's not like LIGO-like detectors, hertz to kilohertz, millihertz. We'll be seeing mergers of supermassive black holes. So these are supermassive black holes with millions of solar masses. They do the same thing. They come closer by gravitational wave radiation reaction and merge, and is going to give you a totally different picture or different class of sources, and you can probe galactic mergers and various things with this again in the next decade. And there will be talk by Sriram and Manjari in the panel discussion about nanohertz gravitational waves. These are even more massive black holes, typically billions of solar masses, or some of the early universe phenomena, which are tracked by, when they pass through the Earth's Earth's atmosphere. We use the existing stable clocks, which are pulsar signals, to track them, and I'm not going to the details of them. They take some time, but this is using timing of the pulsars is what we use to detect them. Because of the high mass again, this will be nanohertz. So we have seen hertz to kilohertz with LIGO, and millihertz with LISA, and nanohertz with this pulsar timing arrays, and they did detect. So I think again this is too complicated a plot, but they did claim a strong evidence for gravitational waves by using a bunch of collaboration. Using this pulsar timing kind of array data, and they are still taking data, and in the years to come, they will improve their significance, and is going to be a extremely important and completely complementary probe of gravitational waves from supermassive black holes with billions of solar mass. So the important difference right now from LIGO, and LIGO is detecting mostly individual sources. Yeah, not mostly individual sources. There's like drops, if you want to think of water drops, whereas what the pulsar timing array is seeing are like a background. There are multiple sources which are superimposed, which is what the pulsar timing arrays are detecting, and you can see this like a rough kind of rough water produced by multiple sources is what pulsar timing array is currently detecting. But at some stage, pulsar timing arrays will reach sensitivity where they can zoom in on some of the sources, but that again may be only with next decade with the square kilometer array and so on. So these are kind of other ways of looking at it. And the last one, which again I think Sriram's talk will talk about, is about early universe, kind of inflationary imprints of gravitational waves. You can look into the polarization of CMB and especially B modes, which are due to the E mode and B mode, which are there, which are considered to be unique signatures of primordial gravitational waves, especially from inflation, which will be an important thing. They will be in 10 raised to minus 16 hertz or something like that, very extremely low frequency. But this is a very, very sensitive measurement, and you need to do the cosmic microwave map into very sensitive region, which will is going to take kind of few more years. So this is showing you again, all in one. So you got LIGO type thing here, and LISA pulsar timing array and CMB here, which goes in the frequency. And one thing is that in between the ground-based detector and space-based detector, you can probe this decihertz detector, which will be between typically 0.1 hertz to say 100 hertz. And I mean, there is some interest to build one in India. There is at least communities trying to convince ISRO to explore the possibility of building something in between the ground-based detector and the LISA detector, and that would mean that LIGO will be here and LISA will be here, and you are like going to probe this void in between these two regions. So this again is among the future kind of ideas, but something which India may be able to contribute depending upon how things come up. Okay, I have 5 minutes. I can, it's important to recall some history about how we arrived at gravitational waves. So, in 1916, Einstein proposed the existence of gravitational waves, and he being him, he was confused himself about they are really physical or some mathematical artifacts of his own theory, which he some point says they are not physical. But people did not believe him, fortunately, and at least in 1957, Hermann Bondi and his collaborators had a very clear, mathematically consistent picture which could prove that these waves are not some artifacts of some coordinate choice, but are indeed physical. That is a very important development in terms of all of this. Then people are starting to wondering how do we detect these waves and how can go about, and some of the Russian people talked about using interferometers as a way, but it was Rainer Weiss who really came up with the back of the envelope estimate about what is it required and how to go about it and so on. In between, Joseph Weber in 1916 claimed a detection of gravitational waves using cylindrical bar detectors. So these are like cylindrical bar which can detect gravitational waves in the frequency, in the resonant frequency of these bars. Unfortunately, his claims were not proven right. So, and but still, it was I think it shows. He was probably over enthusiastic physicist, but it was a very important step in the experimental development. But then it went on, and Ray Weiss and Kip Thorne started talking to each other about what is it required, how to go about detecting or building a detector like LIGO. And as I mentioned, in 1978, this was all efforts were significantly helped by the Hulse-Taylor binary pulsar, which kind of proved beyond existence the gravitational waves do exist. Then, as things went by, in kind of in 1984, LIGO was kind of founded again by Kip Thorne, Ray Weiss, and kind of others. Drever is another figure who played a very important role. And then in 90s, it was considerable, kind of building of LIGO went on. And 2001, is when LIGO started operating. This initial LIGO, this when I started my PhD. Of course, they didn't detect anything. And in 2007, this European detector Virgo started operation in some sense with some sensitivity. But this, this 90s to 2000 is really where all the effort to build this detector has kind of gone in. And 2010 again, as I told you, initial LIGO was shut down, and 2010 to 15 is when the LIGO and Virgo were upgraded. And as I mentioned, 2015, before officially LIGO began its scientific run, we were kind of blessed with this the signal, which is extremely loud signal, as I have explained. And since then, this kind of shows you the developments of what we have seen and where we are headed. I think I have mentioned to you. So it's important to keep in mind that starting from Einstein's own doubts about the waves being physical, we have come a long way, thanks to Rainer Weiss's approach and experimental techniques and his own vision and so on towards building LIGO and detecting gravitational waves and doing astronomy using gravitational waves. And these are all things which takes kind of centuries. But we are here, and we are at the end of at a time when we can make use of the data and to learn new things in astronomy. And yeah, I think that's where we are. So I think to kind of conclude my talk, I think I have mentioned to you why gravitational waves give a new way of looking at the universe and in terms of understanding various issues in the universe. The existing generation of detectors are improving in sensitivity. We have taken some data. I summarized to you what kind of detections we have seen. And in the future, ground-based detectors will be upgraded with Einstein telescope and Cosmic Explorer. LISA will be operational with millihertz sensitivity. Pulsar timing arrays are maturing to detect and characterize nanohertz gravitational waves. And probably an Indian space-based mission in the decihertz will come through. Who knows? And of course, the early universe gravitational waves by using CMB polarization. And in any case, I think the next decade, I think the gravitational waves observations in these various bands are going to kind of significantly enhance our understanding of the universe. And I think these are very exciting times. On that note, I think I'll stop and I'll take questions. I think I was back on time. Thank you so much.
Thank you, sir, for your wonderful speech. The floor is open for questions now.
Yeah.
Sir, the gravitational waves you talked about in initial, like we are facing mix of masses. When a wave passes through them, they are either stretched or straight along some axis. So the gravitational waves are symmetric in our 3D space or 4D space, in which we also consider like time as another parameter. So are they symmetric?
What do you mean by symmetric? So all what I'm saying is that,
sir, if a wave passes through, how will we know that in both of the axes it is stretched symmetrically or strained symmetrically?
yeah. So I think the ring of particle analogy. I'm just so I think the plot I showed you is after taking away. So I'm talking about the two-dimensional. If I have something on two-dimensional thing, how the ring of particle will get deformed. So you are asking the following question. I understand, and let me come back to that question. So you are asking.
It's like a slice of the wave only which interacts in the 2D surface.
Yeah, that is fine. So so the waveform is really talking about that slice. So the Einstein's theory is talking about a wave, orthogonal wave is going by, and I have a ring of particle arranged in a 2D plane, and the waveform, the strain I am talking about from Einstein's theory is about on this ring of particle in the two-dimensional thing. You can ask another question, which is about the symmetry thing, that can there be a mode of gravitational waves which could be like breathing, right? If it expands equally and shrinks in the same way, suppose this is called a breathing mode, which is not allowed by Einstein's theory. But there are theories which goes beyond Einstein's theory, which admits this breathing mode, and which will be you are expecting that your interferometer is going to also breathe out and breathe in, which will not, it will not see any kind of change in fringe, but that is only when it's exactly orthogonal, right? When some angle, it can have a component which will which can do so. Breathing mode can exist in non-GR theories, but which can still be detected suboptimally using LIGO-like detectors.
Sir, one more question. We are essentially detecting the amplitude of the wave, like you said. So which objects in the universe interact with the wave which can decay the amplitude? Because if the wave passes through some distance, it's gonna decay. So how is the decay compensated? How do we know it is?
No, it's not compensated. So I think usually the difficulty with gravitational waves are that these are very weak. Because gravity is the weakest of the fundamental forces, so the difficulties also comes from the fact that they're very weak to interact even with a detector, right? Now you're asking about astrophysically when they propagated from far out, how would it interact with galaxies and intervening matter and so on. So this is exact. I don't know whether Ajit will be talking about cleansing. There can be some kind of distortion to the gravitational waveform due to the intervening matter, though I mean that's a very higher order effect, but you can use those distortions if we have not seen anything yet, but once we detect those distortions, we can use it to probe the intervening matter and matter distribution. So we convert that to an advantage. If you have a model of intervening matter, we would know what kind of distortion to the waveform to expect, and that way you can, it's a probe of the gravitational wave lensing, is a probe of what lies between the source and us.
So it will eventually help us to understand more about the medium and the in-between.
Yeah. When I say, I'm talking about maybe some black holes or galactic clusters and so on, which can interact with it and make small distortions to the waveform. Yeah.
Good morning, sir. We get the graphs of the gravitational waves, sir. How will we know what sort of event has happened in the universe with the graph which we get it?
Yeah, so you're asking if I were to give you the waveform, the waveform such as this, right? I mean, you're asking how did I arrive at the conclusion that this is indeed from 30, this mass and so on, right? So what you do is that, so I told you that what we make use of is that various, we know how the gravitational waves would look like for different masses and spins according to Einstein's theory, which we make use of into a parameter inference. So we cast the problem in the Bayesian language where we try to ask the question, there's a data in the signal, and what kind of, which kind of signals that we can synthesize would match with that. So it's using a Bayesian parameter estimation that we construct a posterior distribution on the masses, which is how it gives you. So we make use of the fact that we have at our disposal waveforms with various masses and spins, which we make use of and to infer what is the mass and spin from the thing. I did not tell about how to do that, but so basically it means that if you have suppose you're finding neutron star signal, that's going to be longer signal in the data, and some will be shorter signal, some will be wiggly signal and so on. So depending upon the mass and spin, the waveform is going to be different, and that is what we make use of to understand it's an inverse problem. We try to infer what are the masses and spins of this thing using kind of casting it in a more general statistical language. That's all.
Does the interference make a standing wave? If it does make a standing wave, what is the time dilation effect we can expect?
Yeah, so I think I told you plus and cross, but ideally depending upon the signal, it will be a combination of both plus and cross, like elliptically. It can be the EX and EY are two polarization of electromagnetic waves, so you can get all kind of polarization, either linear, circular, elliptical, and so on. In a very similar way, you can get linear, circular, elliptical gravitational waves as well. So that's one question. And so I'm saying typical waves we see will have both polarization with some in some kind of fractional contribution. Second thing is when they interfere, of course they'll interfere as a wave, but that is too weak to be detected. But what is more interesting to ask is if there are two signals from two sources give you signals which are overlapping in the data, that does make our issues difficult to analyze the signal, because now your noise on the background and your two independent signals which are overlapping with some thing. This is overlapping signals problem, which will be more of a thing to which is something to be dealt with. This is more important for longer signals, like Lisa would see, for example, signals lasting for years. Okay, so there will be definitely all signals in Lisa will be overlapping. So we need to find ways of addressing how to infer multiple source signals at the same time, and that is a challenge. It's called a global fit problem in the case of Lisa and so on. One has to come up with that, but in terms of kind of interference of two waves, I think that's too weak to be seen any of these things, because it's like a square of the thing. Already signal is weak.
In a broader way, which techniques have you or the LIGO team has used to increase the SN ratio? Because higher the SN ratio, we know the detection is good. So you said we will have thermal noises, and also like seismic activities will also affect it. So which, in a broader sense, which methods do you use to nullify those effects?
So there are two things. One is the improvement from the detector side, right? So you need to suppress the detector noises to improve the sensitivity. Second one is to improve our algorithms and waveforms and so on. These are two ways, because it's a signal and noise combination, right? You need to improve your signal model and improve your noise model. That is what will give you. So in terms of, I'm not an experimentalist per se, but in terms of improving the noises, you need to screen. I think if you want to kind of make the thermal noise to be small, you need to, it's a KT noise. For example, Kagra detector is going to use cryogenic technologies to do suppression. There are various, so LIGO plays with the suspension material, and so there are various material science thing which goes into that. Second thing is about suspensions. The seismic noise is due to suspension, so there are various ways of sophisticated suspension techniques of these mirrors which will improve the thing. And short noise is another one, and you use high power lasers to suppress that and so on. So on these various fronts, we make use of various advanced techniques to suppress them. I'm not highly qualified. On the detector, on the waveform side, we need to, because if the signal is there, the more accurate our waveforms are, the higher will be SNR, because we are putting in more information. So there are still ongoing efforts to improve our waveform models, account for maximum physics that we are not accounting for now and so on. So that is another way of improving the signal to noise ratio. That means including the detection efficiency and so on. So basically including various types of physics into the waveform and improving various technologies to suppress different noise components in the detector.
So we still have like some scope to improve the detector themselves.
Yeah. So I think there's still an ongoing thing. I showed you the. So I think this is where we are. This is where we were, and this is where we are. And O5 is the next observing run in the next 3 years or something. We hope to go from here to here, which means there are well-planned things about how we go about material coating, suspension, and so on. That it takes time to do that, and typically this has to go in steps and steps. After an observing run, we take a break, and there are like 1 year, 2 years of upgrade thing. Then we again operate, because we don't want to detector to not operate for 5 years, right? So it's a combination of astrophysical excitement versus instrument science excitement. We have to find some kind of balance between them.
Are there any other questions? We have about 5-10 minutes. Okay, if not, Arun, I had a quick question. So you said that we could do some test of GR with LIGO India. What's new test of GR?
Yeah, so this is basically polarization test, because in GR we have only 2 polarization, but I think in response to the question I was talking about the breathing mode and other modes, there can be up to 6 modes. And so when you have multiple detectors, independent thing, you can put, you can probe those multiple, the non-GR polarizations to much more tests. You can pause it in terms of null test this null streams and so on, but those are the tests I had in mind about non-GR up to 6 modes of polarization we can probe when we have multiple detectors operating, including LIGO India, and that's good.
And this includes the breathing mode, so
yeah, correct. Yeah.
We will have some evidence for its existence or not. So
yeah, I think. I think even with other Virgo, 2 LIGO, Virgo, and Kagra itself will improve the thing because you need independent data streams. I think LIGO India will add to this ability. That's all.
Could there be better detectors to specifically detect these breathing modes?
There could be, but I don't think anybody will fund it. I'm saying, suppose you optimize the thing for a breathing thing, unless you have some evidence for scalar tensor theory, then I think...
what I was thinking that you mentioned bar detectors, right?
Yeah.
And there are spherical bars. Could they be sort of instrument?
I don't know, but I think the challenge with bar detectors is they're very narrow band. So they can look into some particular range of frequency which may range 100 hertz or something. So that is, because then you may get signals somewhere else. So I not thought about polarization measurements with bar detectors. I knew bar detectors are all, they're not operating anymore, I think. So unless there is some renewed thing to bring them back, I think that may not be a option. But I not thought about the... But I think it is suboptimal. But in principle you can, because if... Yeah. No, I think the strongest evidence, if you have evidence for dipolar radiation, that to me will convince me that one should look more seriously for breathing mode. So you come up with a posterior dipole thing which is peaking away from zero at 90% credibility, we should talk to funding agencies.
And probably you should settle it later with Ajit.
No, I think we are on the same page. I think Ajit is saying it's a difficult thing to do the measurement. I'm saying in principle it can be measured. Anyway, we have many things to settle anyway.
Sure. So if there are no further questions, probably we can move to...
Yeah.
So we have a tea break until 11:15. So please come 5 minutes before that. It's opposite this hall. Actually, it's called Annex Dining Hall. People will be going in that direction, so you can find your way. So we'll come back 5 minutes before 11:15. We'll go for tea now. Thank you. Thank you, Arun.
We are about to begin our next talk. It's my pleasure to introduce to you our next speaker, Professor Sriramkumar. He's a faculty at the Physics Department at IIT Madras. He completed his PhD at Inter-University Center of Astronomy and Astrophysics, IUCAA, Pune, under the supervision of Professor Thanu Padmanabhan. He then pursued postdoctoral research at the Hebrew University, Jerusalem, and then University of Alberta, Edmonton, before joining Harish Chandra Research Institute, Prayagraj in 2001, first as a postdoctoral fellow and later as a faculty member. In 2011, he moved to IIT Madras, where he continues to teach and conduct research. His research spans a broad range of topics in theoretical physics. He primarily focuses on early universe cosmology, that includes inflammation cosmology and the cosmic microwave background, the generation of primordial perturbations, the signature of secondary gravitational waves. His contribution extend to black hole physics, bouncing cosmological models, and so much more. Through this wide-ranging work, he has made contributions to our understanding in the interface between gravity, cosmology, and quantum theory. Please join me in welcoming Professor Sriramkumar.
Thank you, Nidhi, for the introduction. I should begin by thanking Chandra and Arun for organizing this event and inviting me to speak at this event. As a student growing up in Chennai, there were limited opportunities for me to hear about astrophysics, gravitation, and cosmology, so I do not miss an opportunity to speak on these topics. Over the last half a century or so, increasingly precise observations of the anisotropies in the cosmic microwave background have transformed our understanding of the early universe. As Arun would have described, the detection of gravitational waves by merging binary black holes has opened up a completely new window to our cosmos. In addition, as I shall describe during the later stages of the talk, observations by the pulsar timing arrays, which suggest a stochastic gravitational wave background, have the potential to help us determine the evolution, the history of the early universe. In this talk, which is primarily aimed at students, I will describe how the synergy between decades of CMB studies and emerging gravitational wave observations can help us decode the physics operating during the early stages of the universe. Here is an outline of my talk. I'm going to talk about largely during the later stages about primordial gravitational waves which originated in the early universe. In order to understand that, we need to appreciate what is the standard model of cosmology, and that is what my first part of the talk will focus on. For whatever reason, it's very slow. And in particular, I will talk about something known as inflation, which corresponds to a brief period of accelerated expansion during the early universe. And it is during this epoch that the initial gravitational waves, what I will refer to as primary gravitational waves, were generated. And I will talk about how constraints on the inflationary epoch arise from the data of the anisotropies in the cosmic microwave background that I referred to. And I will re-emphasize the points that Arun would have emphasized, namely how gravitational waves, the detection of gravitational waves, provide a completely new window to our universe. And I will focus on two types of generation of gravitational waves. I will talk about what is known as the primary gravitational waves, which are generated from the quantum vacuum during the early stages. And then I will talk about secondary gravitational waves. There are many, many types of secondary gravitational waves. I can talk about them in detail in person, but I will focus on one type of secondary gravitational waves, namely what are known as scalar-induced gravitational waves. All these points will become clear as we go along. And in particular, this is what seems to be, suggested, to be the stochastic gravitational wave background by the PTAs, the pulsar timing arrays. And then I'll close with a quick outlook. So what is the standard model of cosmology? In order to understand cosmology, that is the physics of the universe as a whole, we need to understand what the universe contains. What does it contain? We are not interested in the physics of astrophysics of galaxies or clusters of stars, etc. We are interested, as I mentioned, the physics of the universe as a whole. And when you look at the universe as a whole, there are many, many galaxies in the universe. On the left is what is known as the Hubble Deep Field Image, which is about 30 years old, and every extended object that you see here is a galaxy, and evidently there are many, many galaxies in the universe. On the right is a much more recent, this is 30 years old, as I mentioned. The right one is, less than a couple of years old, and it is called the Hubble Deep Field, the Deep Field, due to the James Webb Space Telescope, and James Webb has been able to observe these galaxies with much more precision than the Hubble Space Telescope could. The bottom line, as far as our story goes, is that there are many, many galaxies in the universe, and in fact, the galaxies are distributed in a fairly, it's not moving. Sorry, it went too far. In a fairly uniform fashion. What you have here are galaxies plotted as a function of distance, okay? And you will see that as you go further and further, there are roughly the same number of galaxies, and though it seems, matter seems clumpy as we look around us, there is some galaxy here, there is no galaxies there, etc. If you, draw a fairly large circle, which, covers a good fraction of the sky, what you find is that there are reasonably the same number of galaxies in these different circles. And if you draw a sphere in the three-dimensional universe with a size of about 80 or 100 megaparsec, megaparsec is about 10 power 6 parsec, a parsec is about 3.26 light years, you find roughly the same number of galaxies in different parts of the sky. And this is best understood from this movie I'm just going to play for you. And this movie was put together by the Sloan Digital Sky Survey, and it goes away from our galaxy, and as you go, as it goes further and further away, you will see two spheres, yellow spheres, one at a distance of about 1 million light years and another at a distance of 1 billion light years. And the first sphere is beginning to appear, and there are very few galaxies within 1 million light years. And one of the biggest galaxies, like the Andromeda galaxy, is located at a distance of about 2 million light years, which will start emerging from the left. And as you go farther and farther away, there are more, many, many more galaxies, and these galaxies are fairly uniformly distributed in the sky. And eventually, you will see a pattern in the sky, which is known as the anisotropies in the cosmic microwave background. That is the Andromeda galaxy, and you will see further galaxies, more and more galaxies as this movie goes further and further in terms of distance. And the bottom line is that the galaxies are smoothly distributed in the universe on suitably large scales, and therefore, in order to understand the structure in the universe, the distribution of galaxies in the universe, we would like to divide it into a homogeneous part or a smooth part and a part which involves perturbations, which are small deviations from homogeneity. And there are good reasons to believe that this description is valid, as I will explain as we proceed further with the talk. So there are many, many galaxies in the sky, and in fact it will take a swing around in different directions to illustrate the fact that it is not just, in one particular direction. In whichever direction you observe, there is a remarkably uniformly distributed number of, the galaxies are distributed remarkably uniformly in virtually all directions of the sky. And I talked about the cosmic microwave background, which will appear in a couple of seconds. And that will form a crucial part of the first part, crucial part of my story during the first half of the lecture. I'll just let the movie play out. So those all correspond to galaxies. Each dot represents a galaxy in the sky. And what I was saying is that if you draw a sphere which is reasonably large, of the order of 80 to 100 megaparsec, and you count the number of galaxies in the sky, they are roughly the same in different directions. And these blue, yellow, and red and green spots that you see correspond to what are known as the anisotropies in the cosmic microwave background. They are located at a certain distance in the sky, and they will form an integral part of this talk, the first part of the talk at the least.
These are made from some cosmology simulations, is it?
No, this is actual observations.
As comparing observations at different scales?
Yes, absolutely. This is a movie based on this set of observations. This is just a projection that has been shown. So there is matter in the universe. What else is present? There is radiation present in the universe. There is light from the stars. And you would naively imagine that the light from the stars, from different stars that constitute the galaxies, would dominate the amount of energy in the radiation, energy density in the radiation. Not quite so. If you plot the intensity of radiation as a function of different frequencies here, okay, what you find is that they peak at a particular location. This is not working so well. At a particular location in the spectrum. And it is in the, actually, the peak occurs in the microwave region of the electromagnetic spectrum. And this happens to be something known as the cosmic microwave background. What do we have? We have this radiation coming to us from virtually all directions of the sky. We are bathed in it. Even as we stand here, there are microwave background, photons from the microwave background, which are, scattering off us as we speak. And that dominates, that contribution to the energy density from the microwave background dominates every other energy density that you have in the electromagnetic radiation in this universe. And in fact, if you zoom in into this part of the electromagnetic, spectrum, what you find is that this, the radiation from the cosmic microwave background is remarkably perfectly Planckian. In fact, it has a temperature of about 2.725 Kelvin, and these error bars that you see have been increased about 200 times, so they are visible in this plot. So it's a remarkably perfect black body spectrum corresponding to that temperature, and as I've said, the error bars have been increased so many times, so that, a few hundred times, so that they are visible in this plot. So what do we have? We have matter in the universe. We have radiation in the universe, and and the radiation, the dominant part of this radiation is in the form of a thermal black body radiation that is present everywhere in the universe, and this is known as the microwave background radiation, and it is cosmic, and therefore it is referred to as the cosmic microwave background radiation, or CMB or CMBR. And what else do you want to know about the universe? Well, what else do you know about the universe? Well, the galaxies seem to be running away from us. What you can do is that measure the spectrum of these galaxies, and this is the spectrum from a typical star or a collection of stars in our own galaxy. And you look at galaxies at which are farther and farther away, and what you find is that the spectrum is shifted towards the red end. What it means is that if you compare this spectrum and the spectrum, you find that the spectrum as a whole is shifted. Of course, if you have a single line, you will not be able to observe this shift. But galaxies have very typical spectra, as you can see, and you can compare different spectral lines corresponding to different elements, and the pattern of these spectral lines across galaxies which are very similar in other properties. And what you find is that the farther the galaxy is, the faster it seems to be moving away from us. The wavelength, the spectra of these galaxies are shifted towards the red end of the spectrum. And if we want to interpret that in terms of the Doppler effect, what you essentially will interpret it as though they are moving away from us. And importantly, what you find is that the farther they are away, they seem to be shifting to, the spectra seem to be shifting, towards the red end of the spectrum by a larger amount. Well, what essentially happens is as follows. On these larger scales, your Newtonian theory of gravitation is not valid. You need to use a new relativistic theory of gravitation, which was originally proposed by Einstein, and it is known as the general theory of relativity. And when you apply this theory to this scenario of this universe, and you examine what happens to a photon, what essentially happens is that if the universe is moving up, expanding, then what you can immediately show, all the photons in the universe will exhibit redshift, or in other words, that energy will decrease with time depending on the manner in which the universe expands. And in other words, the redshift that I was talking about in the previous slide is not due to the Doppler effect as I originally tried to explain. It is due to something known as cosmological redshift. It arises, it's known as cosmological redshift, and it arises due to the expansion of the universe. How do you visualize this expansion of the universe? Well, between this space, or the space-time between two of us are not changing with time. We are bound together, to the Earth, and the Earth itself is bound to the solar system, and the solar system in turn is bound to the galaxy. The galaxy in itself is not expanding, but the distances between the different galaxies are changing with time, and in fact it is increasing with time. And one can show using general relativity, what you can show is the following. What it says, what general relativity essentially says is that the space-time, becomes curved because of matter present in the universe. Think of a rubber sheet. I'm not able to use this pointer well. Okay. Think of a rubber sheet and you place a ball on top of it. What essentially happens is that the rubber sheet was, in the absence of the ball, was flat, but the moment you place a heavy ball on this rubber sheet, it sort of becomes curved. And now if you drop a smaller ball in this rubber sheet, such as a marble, then what happens is that it begins to move in the manner in which the space-time or the rubber sheet has been curved by the presence of the large ball. And in the same fashion, a photon moving in the universe sees the effect of the matter and every type of matter, radiation present in the universe, and this matter that is present in the universe is causing the universe to expand. And because of the expansion, the photons lose energy, which is what, as I mentioned, we observe as cosmological redshift. And what we are also trying to understand is that how does the matter affect the evolution of the universe? In other words, by determining the history of the universe, the manner in which what happened to the universe at different epochs, we are in some sense trying to understand what is the matter content of the universe, and this is described by what are known as the Einstein's equations. The Einstein's equations relate the content of matter to the manner in which the space-time itself behaves or is curved. So, using the Einstein's equations, you can determine how the energy density of different components of matter in the universe changes with time. We talked about the presence of matter. The galaxies consist largely, not quite, they consist of something known as cold dark matter as well, but they, for our purposes, behave in the same manner as matter that you and me are made of, which the cosmologists refer to as baryons. So there is matter present in the universe, and there's radiation present in the universe. There are other things also present in the universe, particularly something you would have heard about, something known as the cosmological constant. That will not play a large part in our story, but we will talk about accelerated expansion very soon. So now you have matter present in the universe and radiation present in the universe, and you can turn to general relativity to ask how they behave with the expansion. And you know that the energy density of matter goes as 1 over the volume. Okay? In other words, 1 over cube of the size of the universe in some fashion, if you want to say it in some fashion. You can show using general relativity that the energy density of radiation changes as 1 over, not the volume power 4 by 3 instead of volume itself. It goes faster. In other words, the dilution of the energy density of radiation in the universe is faster than the dilution of matter in the universe. Today, there is matter and radiation present. I mentioned how the radiation is largely in the form of the cosmic microwave background. But if you run this, and the universe is expanding, and if you run this movie, if this picture backwards, what you essentially find is that at very early times, there was more energy in the radiation than that of matter. And you say that the universe started in a hot, dense state. And in fact, if you push these arguments back, if you push this energy densities, back, and you hit a singularity, the energy densities diverge, and this singularity is often referred to as the Big Bang. And this is a singularity which cannot be explained by, general relativity predicts it, but general relativity is not adequate to deal with the singularity. You need some other theory to help us understand what exactly happens at the Big Bang. Nevertheless, what you have essentially is a model which suggests that there was a Big Bang where the energy densities of matter and radiation were infinite. The energy density of radiation dominated that of matter, and therefore the energy started the universe started in a hot, dense state. This is in fact the title song of this sitcom called, serial called the Big Bang Theory. And this is the first line that appears as a part of the song. Our universe was in a hot, dense state. It cooled down as it expanded, and there comes an epoch when the energy density in the matter begins to dominate, that of radiation. Sometime around this epoch, what essentially happens is that the photons stop interacting with the electrons. Think of an early situation where there was, sufficiently high energy density of radiation that is described as this yellow fluid in this picture. There are also green and blue balls. The green and red balls. The large red balls are protons. The small green balls are electrons, and the large green balls are neutrons. And essentially at a high enough temperature, what happens is that these photons knock off the electrons which are trying to combine with the protons. This I hope you recognize is essentially a proton, or in other words a hydrogen nucleus. This consists of 2 protons and 2 neutrons, and therefore is a helium nucleus. At sufficiently high energies, these photons do not allow the electrons to recombine with the protons. But as the universe cools, there comes a temperature, not at the time where the transition from radiation to matter domination takes place, but slightly later due to some other, the details arise due to the distribution of the photons, thermal distribution of the photons. What happens is that at a temperature of about 3000 Kelvin, remember the universe is at a temperature of about 3 Kelvin today. Remember, that's the temperature of the CMB. And what I did not explain is that the relation between the temperature and the size of the universe, but I had indicated as to how the energy density of the radiation goes, higher and higher as you go back in time. And remember, if you have a thermal distribution of photons, you know that the energy density of radiation is determined by the Stefan-Boltzmann's law, which indicates that the energy density goes as is proportional to T power 4. And if the energy density of the radiation goes up as you go back in time, evidently the temperature will go up as well. And you can show that the temperature is proportional in some sense to the, inversely proportional to the size of the universe at a given time, or the distance between any 2 galaxies at a given time. And what you essentially, I was not precise in those statements. If there are questions, I'll clarify at a later stage. So the temperature, when the temperature was about 1000 times larger than the temperature today, what essentially happened is that this transition occurred where the electrons start combining with the protons, and they form, as you can see, this is a hydrogen atom, this is a helium atom. And what do the photons do? The photons do not have enough energy to knock off those electrons. They start streaming freely towards us, which is what we observe as the cosmic microwave background. In other words, the cosmic microwave background is nothing but the vestiges of the radiation that was present in the early universe. It was always present in the universe, and it is coming to us, from this time, which is called as the last scattering surface, as I try to explain in the next slide. Think of a situation. Here, what do you have? You have these electrons which are, here you have the electrons are strongly interacting with the photons. But there comes a time when the electrons stop interacting with the photons. So in other words, the electrons have a very short mean-free, the photons have a very short mean-free path during this epoch because they are constantly being scattered by the electrons. But there comes a time when the photons are hardly affected by these electrons and they start streaming freely to become the CMB that we observe. And what happens here? So think of a photon in the cloud of, above us, in the sky. what essentially happens is that the photon is constantly scattered by the water molecules, but when the thickness of the cloud is sufficiently small, what essentially happens is the photon starts streaming freely towards us, and you observe essentially the edge of this cloud as the cloud. And similarly, so what you have is the photons coming to us from all directions of the sky, virtually all directions of the sky, and as you keep looking at the universe in different directions, as you probe deeper and deeper, since light takes a finite amount of time to travel, as you look deeper and deeper, you are essentially observing, the universe as it was older and older, and as you will go in some direction, you will in fact hit the Big Bang singularity. But the CMB photons comes to us from this time when the matter stops interacting with the photons, and the photon starts freely streaming towards us. And by observing the temperature distribution on this surface, which is called the last scattering surface, you can in principle determine the physics that happen behind this. And much the same thing will occur in the context of gravitational waves, as we will come to during the later part of the story. And remember, if you have different temperatures on the surface of the Earth, you can project the temperature on this projection, which is often referred to as an ITAF projection. In much the same manner, the temperature on this last scattering surface, the surface is present in all directions of the sky, all 4 pi, solid angle of the sky, and you can project it on as, the temperature of this last scattering surface in a similar manner, much like you project the temperature on the surface of the Earth. And what you observe, as I mentioned, is that the temperature is more or less the same in all directions of the sky. But if you start looking at the 5th decimal place or so, you start observing differences in the temperature in different directions of the sky. In other words, the temperature of the CMB is largely anisotropic to 1 part in 10 power 5. But if you start measuring the temperature at the 5th or the 6th decimal place, you start measuring the anisotropies in the CMB. In other words, at the 5th decimal place or beyond the 5th decimal place, you start seeing the differences in the temperature in different regions of the CMB sky. And this has been measured to greater and greater precision over the last 20, 30 years or so. And what you essentially have is an observations from the early 90s, and this has been measured to better and better precision, originally by W. and later by Planck, and which tells us, helps us understand the physics behind this curtain of CMB. This is where the inflationary scenario comes in. There are 2 questions to answer. Why is the CMB so isotropic? Why is more or less the temperatures in different directions are the same? And how did these anisotropies arise? This is the challenge for us to explain. Now you can ask whether a particular region in the CMB sky, say 1 degree in the sky, is causally connected by the time of the CMB. What one finds is that any 2 regions in the sky within the hot Big Bang model, we have already understood there was a period of radiation-dominated universe, and the universe cooled down to transit to something known as a matter-dominated universe, where the radiation stopped being the dominating form of energy density in the universe. Using this history, we can ask what is the domain of causally connected region in the sky. And you find that causally connected region, if it had been the entire sky, you can explain within the hot Big Bang model, you can provide a mechanism to say how did these anisotropies arise. But what you find is that only regions which are about 1 degree in the sky are causally connected. I will explain this better using a different picture in the next slide. And what you find is that in fact regions which are separated by more than 1 degree in the sky, which are widely separated, are not causally connected within this hot Big Bang model. Then there arises the question, how is the temperature in this direction of the sky the same as this direction of the sky? And there is another way of understanding. What you draw are light cones. Okay, in a curved space-time, the light cones are not at 45 degrees, but you can choose your coordinates such that the light cones are at 45 degrees in the expanding universe. And this is today, this is the epoch of Big Bang, and this is the time of last scattering when the CMB starts streaming freely towards us. And you can draw a forward light cone from the time of the Big Bang, invert this blue light cone, And you can, draw a backward light cone from today up to the epoch of the last scattering surface. And what you essentially find is that this forward light cone is much, much smaller than the backward light cone. And it is this forward light cone which subtends an angle of 1 degree in the sky. In other words, widely separated regions on the last scattering surface could not have causally, interacted before, from the time of Big Bang until the time of decoupling, when the CMB starts streaming freely. And therefore, there is no mechanism within the hot Big Bang model to explain this sense of isotropy, the extent of isotropy of the CMB. But what happens is that if you have an epoch of inflation, if you have an epoch of accelerated expansion, this is somewhat technical, but you can show that this time of the Big Bang can be pushed behind, and you can have a situation where the light cone, the forward light cone, can be as big as the backward light cone, and therefore you can explain the extent of isotropy of the CMB. What you essentially require during the early stages of the radiation-dominated era, an epoch of accelerated expansion, which can ensure that the forward light cone is as big as the backward light cone. And this epoch is known as inflation. What essentially occurs is as follows. This has been, this is time plotted from the Big Bang. That's the Big Bang, and this is today. And this is the scale of the universe, the size of the universe, or in fact separation between any 2 points in your universe. And this is the radiation-dominated era, and this is the matter-dominated era. At very early stages, roughly about 10 power minus 35 seconds after the Big Bang, you need an epoch where the scale factor, remember that this is represents the change in the size of the universe, or the distances between any 2 galaxies of the universe, and that has to increase by a tremendous factor over a short period of time. In fact, it has to increase by a factor of about 10 power 30 within an extremely short fraction of time, and that is often referred to as inflation. But the problem is that the matter and radiation in the universe cannot help you achieve that epoch of inflation. You need to turn to some other objects called scalar fields in the universe. And there are many scalar fields that are present in high energy physics. You can turn to one of these fields to achieve this rapid expansion that I talked about, accelerated expansion that I illustrated in the previous slide. What you can think of when you talk about a scalar field evolving in the universe, you can think of a particle in classical mechanics that is, rolling down a given potential, and you can, what has been plotted is the evolution of such a scalar field. What the expansion of the universe does is essentially induces friction in the scalar field. In some sense, it is like a mechanical particle that is moving along a potential but added friction. And essentially, if you plot the phase-space trajectory of the scalar field, what you arrive at is like you have an attractor. So, and if you had plotted the phase-space trajectory of a damped harmonic oscillator, what will happen is that instead of an ellipse that you will have in phase space in the context of an undamped oscillator, instead of that you will have a spiraling, a path which is spiraling into the origin here, and that is how the scalar field evolves in an expanding universe. And if you have these scalar fields, what you can do is that you can achieve inflation. You can ensure that there is a rapid expansion of the universe through a very short period of time, and that will ensure that this entire region of the CMB sky that you are observing is causally connected by the time of decoupling. And what happens is that these scalar fields naturally contain quantum fluctuations. They are intrinsically quantum, and therefore they will always have these quantum fluctuations, and these quantum fluctuations in the scalar fields are primarily responsible for the anisotropies in the CMB. And as far as technical details are concerned, you can relate the perturbations in the matter and the fields and the space-time coordinates, in the space-time geometry rather, through the Einstein's equations. And there are different types of perturbations. The perturbations that you are familiar with are perturbations in the energy density and pressure of matter, and they lead to the largest anisotropies in the CMB that I talked about. But tensor perturbations or gravitational waves, which is what we wish to talk about, are also produced during inflation, and they are in fact produced even in the absence of sources. And these tensor perturbations are what we will refer to as primary gravitational waves generated from the quantum vacuum during inflation. What essentially happens is as follows. This is a simple way of imagining how these perturbations are generated. Initially, the universe is smooth. There are no perturbations. That is, the energy densities are constant everywhere in the universe, energy densities, pressure, etc. But there are small, tiny fluctuations that arise due to quantum fluctuations. And what essentially happens is that it is these quantum fluctuations that are responsible for the small anisotropies in the CMB. And the fact that the CMB anisotropies are small to 1 part in 10 power 5 is what allows us to divide our universe. Remember, I told, for convenience, mathematically, we divide the universe into homogeneous part. We understand the evolution of this background, which consists of a Big Bang, radiation domination, and later matter domination. And that's the smooth background part, on top of which we need to understand how the inhomogeneities or perturbations arose in the first place, and how did they leave imprints as anisotropies in the CMB, and how did they become the large-scale structure that we observe around us today, that we saw in the Slow and Digital Sky survey as galaxies and clusters of galaxies. We will not go that far. Our primary goal is to understand the CMB. I hope you understand, you appreciate, it is these quantum fluctuations that induced some inhomogeneities in the early universe, and they evolved to cause the anisotropies in the cosmic microwave background. So just a slight detail, what you have is as follows. I'm significantly behind. I will catch up, I will skip some slides and catch up eventually. This picture is somewhat important for us to understand, because the later part of the talk will become a little technical for me to convey what are primary and secondary gravitational waves. I've already talked about primary gravitational waves. These are the gravitational waves that are generated during inflation. Much like the case of electromagnetism, gravitational waves can also be generated in the absence of sources, and these gravitational waves are generated from the quantum vacuum during inflation. What has been plotted here is the wavelength of the perturbations. You have a homogeneous background, and you are interested in studying the evolution of these perturbations. Perturbations are quantities which are dependent on space, and you know that even if you study waves in a flat space-time, for instance, how do you study them? You go into a Fourier space and study the evolution of each mode in this Fourier space. And what you essentially have here are the wavelengths of these modes in the universe of gravitational waves or scalar perturbations or any quantity which is dependent on space and time in the universe. And what has been plotted in green is what is known as a causally connected region at any given point of time. What you have is that at very early times, this corresponds to an epoch of inflation. If you don't have an epoch of inflation, you will not have a causally connected region in the early stages of the universe. I didn't have time to emphasize this point adequately, but if you have an epoch of inflation, they can be inside this causally connected region. That is why you needed to introduce an epoch of inflation in the hot Big Bang model. If you have an epoch of inflation, they can emerge from inside the Hubble radius, and they can leave the Hubble radius. And what will happen is that this is when they will have their impact on the CMB, and they will have impact on the large-scale structure, and they will create the patterns in the CMB and the distribution of the large-scale structure. And this evolution corresponds to both scalar perturbations, that is density or pressure perturbations, as well as gravitational waves that could have been generated in the early universe. So what you have, as I will describe later, are gravitational waves that will be observed today, that what has been generated during inflation will leave their imprints on the CMB, but those gravitational waves, after leaving their imprints of the CMB, they will also, on smaller scales, evolve today, and we can in principle observe them and ask what is the strength, what is the energy density in these gravitational waves, and whether they can be detected by one or more of the gravitational wave observatories that Arun would have talked about, and I will talk about as we proceed. So some essential properties Arun would have mentioned of gravitational waves. They are transverse in nature. They are essentially small disturbances or ripples in space-time which travel at the speed of light, and they satisfy the wave equation in a given background space-time. So all you need to do is that solve the evolution of in order to understand how the gravitational waves generated during inflation, how will they be today? All you need to do is solve these wave equations at different epochs and match those conditions at the different epochs as you go from one epoch to another. And as I mentioned, gravitational waves are transverse in nature, and they're characterized by 2 degrees of polarization. I presume, Arun would have talked about what is the impact of a gravitational wave on a collection of particles, and these correspond to the 2 polarizations of the gravitational wave, plus and cross. I can play this GIF, but I presume you know what they are. Now we talked about what we would like to understand is that how can we constrain the strength of gravitational waves generated during inflation. But what happens is that the largest impact on the CMB is not actually due to gravitational waves, but due to the matter perturbations or density perturbations or pressure perturbations. So there are what are known as scalar perturbations, which are the density and matter perturbations. I can explain later in person as to why they are referred to as scalar perturbations. And the gravitational waves are tensor perturbations because they arise in what is known as the space-time part of the metric. So you can characterize the scalar perturbations, you can characterize the tensor perturbations. We haven't, as I will describe, we haven't yet seen the imprints of the tensor perturbations, and therefore we are not interested in these details. We are interested in essentially the amplitude of the tensor perturbations. We know the amplitude of the scalar perturbations very well from the amplitude of the anisotropies in the CMB. So what we are essentially interested in determining something called NS, which is something which describes the spectrum of the scalar perturbations, and something known as the amplitude of the tensor perturbations or the tensor to scalar ratio. So what do you have? You can try to arrive at constraints on these parameters from the CMB data, the cosmic microwave background data, that is the measurements of the anisotropies in the cosmic microwave background. So what you have is essentially a theoretical curve plotted in blue and the error and the observations plotted in red with error bars. And this has imprints of both the scalar and tensor perturbations, and you can arrive at constraints. I'm sorry, I went there a little far. And what you essentially find is as follows. We know this, scalar perturbations fairly well. Remember, this NS describes the scalar perturbations or density perturbations, and what we are interested in understanding how much of gravitational waves that were generated during the early universe. We don't have direct observations of these gravitational waves generated during inflation, the primary gravitational waves, but we have an upper bound on how much they contribute to the anisotropies in the CMB. And in fact, the holy grail of cosmology is attempting to measure the precise amplitude of the gravitational waves generated during inflation, because if I can determine the strength of these gravitational waves, I can know exactly at what energy scale, at what time scale did inflation occur. But we haven't yet measured these. We have upper bounds, as I will describe in the next 2 slides. Earlier, I talked about the anisotropies in the temperature of the CMB. That is, when I measure the temperature in different regions of the CMB sky, they will have differences, and I can convert into a Fourier transform on a spherical space, which is what the angular power spectrum that I plotted a couple of slides back was all about. In addition, the electromagnetic waves are polarized, and on the sky, it is convenient to decompose in terms of what are known as E modes and B modes. There are 2 types of polarization. The E modes are much like divergences. They are like electric fields. The B modes are generated largely due to gravitational waves, primordial gravitational waves, and they have a curl-like structure, much like the magnetic field, and therefore they are termed as E and B modes. So in principle, I can measure the strength of these B mode polarization, and if I can measure the contribution on the largest scales or the smallest or the largest angular scales, then I know the extent of primary gravitational waves generated during inflation. And this has been going on for the last 30 years or so, and there are better and better constraints. We are yet to see their direct imprints. Okay, so what you have is something known as the B mode polarization of the cosmic microwave background. What you are essentially trying to do is determine the strength, not in the temperature, but in a particular polarization of the electromagnetic, of the photons that come to us from the CMB, and what these are upper bounds. And this particular thing is what is possibly going to be measured by LightBird if the primordial amplitude of the tensor perturbations were about 1/100th of the scalar perturbations. I've already told you how the amplitude of the scalar perturbations are well measured, but if the contribution to the strength of the perturbations, the tensor perturbations contribute by about 1% of the scalar perturbations, then it can in principle be seen by a forthcoming mission such as LightBird. And what you have here is what is known as the primary CLBB, that is the angular power spectrum generated due to the tensor perturbations, induced from the vacuum, during inflation. At larger, multipole moments, there is another effect due to scalar perturbations that I will not have time to talk about. So if you are able to measure this, then in principle, you would have seen the primary gravitational waves. And what has been plotted here is this is the instrument noise of this LightBird mission that I talked about. And this, corresponds to a tensor to scalar ratio of 4 times 10 power minus 3. So you're talking about something like 0.4% of the scalar perturbations. If they have that amplitude, if the tensor perturbations that have that amplitude, then it can be detected by a future mission such as LightBird. And if you see this, you will essentially know the energy scale of inflation. If you have heard the story from something called BICEP about a decade back, they declared they have seen these effects, only to take that declaration back, and we are yet to see the direct, imprints of the tensor perturbations on the CMB polarization. So we have a timeline for our universe. There was a Big Bang. This corresponds to the manner in which the universe is expanding. It was expanding rapidly fast during inflation. It is during this epoch you had these quantum fluctuations that generated the perturbations in the energy densities and also gravitational waves. And sometime later, the age of the universe, as you may know, is about 13.7 billion years. When the universe was rather young, about 400,000 years or 380,000 years to be precise, that is when the decoupling occurred. And that's where you observe the CMB from. And by observing the CMB, you are trying to construct what happened to the universe behind the screen of the CMB. And there was matter domination when the galaxies form, and there is a late time acceleration where, a story you will hear about it in another talk. This is a more dramatic timeline of our universe. There was a Big Bang. We don't quite know what happened prior to about 10 power minus 43 seconds or so, because you need a quantum theory of gravity. Sometime later, around 10 power minus 35 seconds, you had inflation. And inflation transited through a process known as reheating to an epoch of radiation domination. And the radiation domination, lasted until about 300,000 or 380,000 years. Many things happened during this epoch. And we will see, I have very short time, but I will try to explain how, we can try to construct this epoch of the universe through observations of gravitational waves. And later, you had a matter domination, etc. And we will come back to the previous slide a little later. That's what the CMB tells us about the early universe. As Arun would have explained to you, gravitational provide a completely new window. He would have talked about LIGO. I'll skip these slides for want of time. He would have talked about how merging gravitational waves were observed by LIGO, and we are celebrating 10 years of this detection. And this is the On top, you have the actual measurements. At the bottom, you have the waveforms as constructed using numerical methods. And this corresponds to, a particular detection at certain frequencies of about a few tens of hertz up to a kilohertz or so. That's the LIGO band of frequencies. But there are many other sources, as Arun would have explained, in the universe, which will emit gravitational waves at different frequencies. You can have situations where, you're talking about rotating neutron stars or supernovae, which can emit gravitational waves over a certain range of frequencies. You can have merging supermassive black holes, which can emit in what are known as the nanohertz range of frequencies, somewhere here. And where is the frequency? Here, 10 power minus 9 or few times 10 power minus 8, etc. And I will talk about that in due course of time as observed by the pulsar timing arrays. I've been talking about extremely small frequencies which, the CMB can constrain. And what I want you to appreciate is that, while these astrophysical sources that Arun would have talked about emit typically at higher frequencies and over a narrow band of frequencies, the quantum fluctuations in the early universe, or, in general, gravitational waves generated in the early universe through not localized mechanisms, but mechanisms which occur over the entire universe, generate gravitational waves over a wide range of frequencies. There are many, many possibilities. I'll be talking about only two of them. I've already talked about one of the two, namely generation of gravitational waves from the quantum vacuum during inflation, which is what we refer to as primary gravitational waves. Here is yet another picture, another image, more modern image, okay? And again, the point to emphasize is that the early universe generates gravitational waves not over a localized range of frequencies, over a wide range of frequencies. And one of the things you would like to ask is what happens to the gravitational waves during inflation? How will their spectrum look today? I already mentioned as to how the evolution of the gravitational waves depends on the nature of the background. If you are studying them in a radiation-dominated universe, they will behave differently. If you are studying the gravitational waves, I'm talking about the gravitational waves generated in the early universe, not what Arun was talking about. The gravitational wave generated from the vacuum during inflation, quantum vacuum during inflation, will evolve during different epochs depending on the manner in which the background is changing with time. And what you can do is as follows. Much in the same manner as the CMB tells us, has a last scattering surface. It is the last scattering surface because of the fact that, that is when the photons stopped interacting with the electrons and started freely streaming towards us. Gravitational waves are small disturbances in the space-time, and they always interact weakly with matter, and therefore, whenever they are generated, they could have been generated during inflation. This corresponds to the epoch of inflation. These could be primary gravitational waves generated during inflation, and they will hardly be affected by the matter present in the universe, and they can have some small effects when they have something known as anisotropic stress, but they are largely unaffected, and therefore they travel to us virtually freely. And as a result, instead of 380,000 years when the CMB arose, in some sense, started streaming freely towards us, by measuring the CMB, we are essentially determining the distribution of the density, energy density of radiation at that time, or the temperature at that time. And from that, we are trying to reconstruct what happened to the universe before that epoch. The observations of gravitational waves will tell us how the universe evolved from the time of generation of these gravitational waves. It depends on what type of gravitational waves you are talking about. From the time of the generation, and they in principle carry information about the evolution history of the universe. So by observing the gravitational waves, I can in principle construct the history of the universe much prior to the epoch of the last scattering surface of the CMB. In fact, I can probe the universe as early as about 10 power minus 35 seconds or so. And that's the power of gravitational waves. And So, as I said, I will talk about two mechanisms for generation of gravitational waves in the early universe. First, I have already talked about. These are the primary gravitational waves that are generated during, during inflation. I talked about how inflation corresponds to essentially a scalar field or a ball rolling down a potential with friction thrown in. And what happens, during this epoch? This part, when the ball is rolling about some part of the potential away from the minima, it leads to inflation. It leads to an accelerated expansion of the universe. But what one finds is that when the ball has rolled towards the minima, inflation is naturally terminated. Inflation stops occurring, or the universe stops, acceleration and transits to an epoch of, decelerating universe. Transits to an epoch of deceleration. And during this period, what essentially happens is that the radiation in the universe has tremendously cooled. There is radiation present even during this expansion, and one can show using the behavior of photons in an expanding universe that the temperature, this I have already indicated, temperature of the universe falls with the expansion. Therefore, the radiation present during inflation has cooled down tremendously by the end of inflation. And what you need to do is that you need to reheat the universe. You need to, you want to restore the hot Big Bang model, which otherwise has worked well for you. And therefore, you need to reheat the universe. And this occurs as the field is oscillating, indicated in these red balls at the bottom of the potential. As it oscillates, you can set up a mechanism to transfer this amount of energy that is present in inflation to radiation. And this is an epoch known as reheating. And during this epoch, what you can show is that you can have multiple epochs of reheating. One happens immediately after inflation, and an epoch of reheating can in principle occur much later due to the presence of additional fields. I can describe the details in person if you are interested. And you can, as I mentioned, the gravitational waves generated during inflation, you can evolve them through the different epochs and ask what is the energy density of these gravitational waves. Today, this quantity you will repeatedly see is what is known as the spectral energy density of gravitational waves. It's a dimensionless quantity. It roughly reflects, in some sense, like the intensity of radiation that you may know in the context of electromagnetism. It is just divided by the total energy density of the universe to make it dimensionless. To be precise, it is the energy density per logarithmic interval in frequency divided by the total energy density of the universe, if you want me to be precise about it. And what has been plotted is this quantity that arises today for different histories of a universe. So what essentially happens is that there is a particular type of reheating which leads to a spectrum of this type. If you have, a different type of reheating mechanism, it can lead to a rise in the spectrum of these gravitational waves, in the spectral energy density of these gravitational waves. And what I have also included in the plot is the sensitivity of the different gravitational wave observatories. And, Arun would have talked about the sensitivity of LIGO, which is indicated here. It's very high. But in principle, you can see by observations of LIGO, in fact, there are constraints on such a background of gravitational waves from the LIGO-Virgo collaboration, which suggests that certain things which passes through LIGO is ruled out. Okay, so the primary gravitational waves generated during inflation, can constrain in this manner. In fact, it is only determined by the history of the evolution of the universe. Okay, and that evolution determines the strength of these gravitational waves, and therefore, by arriving at stronger and stronger constraints on such a background, what is often referred to as a stochastic background of gravitational waves, I'll make a few further remarks as we go along, you can constrain the history of evolution of the universe. Chandra, I will take 7 minutes. Okay, I'll try to wrap up as much of the next part of the story as possible. So I talked about one type of gravitational waves, the gravitational waves generated from the quantum vacuum during inflation. Next, I will turn to what are known as gravitational waves induced by scalar perturbations. I will try to explain it as well as possible. The story sort of goes as follows. This is a picture that I'm sure Arun have shown again. What do these correspond to? These correspond to mergers of binary black holes in the universe. And for astrophysicists, who was trained in astrophysics prior to the detection of gravitational waves, these range of masses were rather unexpected, to say the least. And the question was asked whether these black holes could have formed, not due to astrophysical processes at late times in the universe, could they have formed in the very early universe due to extremely high energy densities created, say, due to inflation. The point is as follows. We talked about the evolution of these wavelengths of the perturbations at in an earlier slide. I don't have time to go back to that slide. Remember, I talked about the evolution of a causally connected region, which is indicated by this. Okay, to be precise, it's called the co-moving Hubble radius. And I talked about the wavelength of these perturbations, right? When you're studying waves or anything that is propagating in a smooth background, you will Fourier decompose and study the evolution of these individual Fourier modes. And that's what these different wave numbers correspond to. So what do you have? I talked about how if you have an epoch of inflation, these wave numbers can be inside a causally connected region and you can impose well-motivated initial conditions on these perturbations. This is during inflation. I talked about how at the end of inflation, you will have an epoch called reheating where the energy density from inflation is transferred to radiation. And then you have an epoch of radiation domination universe. Okay? And the CMB is observed over large scales, very large scales of about, something like 1 megaparsec to about 10 power 4 megaparsec, which is this causally connected region today in the universe. Those correspond to here. They leave the Hubble radius at early times and re-enter at later times. But if you have a situation where on very small scales, scales which are of the order of about something like 10 power minus 7 megaparsec inverse. I will let you do the math about what a megaparsec inverse is and what this scale corresponds to. And if they have enough power on these scales, what happens is that when they re-enter, they can collapse to form primordial black holes. So what you essentially need, this is, I have been repeatedly pointing out as to how the CMB constrains the strength of the density perturbations and pressure perturbations. We know their amplitude very well, but I know their amplitude only on large scales. I talked about these numbers of about 1 megaparsec. This is in inverse megaparsec units. 1 megaparsec to about 10 power 4 megaparsec, over which we know the strength of the primordial perturbations fairly well. But on much smaller scales, there are no such constraints. Now you can ask, could these black holes have been generated in the early universe? I can do so provided the power, the strength of the primordial perturbations in Fourier space goes from this strength to a strength like that. Then I can form enough number of primordial black holes in the universe, and what you need is complicated dynamics during inflation. If you recall, I had drawn the phase-space trajectory of scalar field during inflation earlier. I talked about how it resembles the phase-space trajectory of a simple oscillator but damped. But now if you introduce, earlier it had come like this and essentially fallen into the origin. But if you introduce non-trivial dynamics during inflation, okay, which can be generated by not by a smoother potentials that I talked about, but by much more complicated potentials, you can have non-trivial dynamics during inflation, and they can in turn lead to spectra which are fairly non-trivial. I talked about earlier how, you have on large scales, over scales something like this, this is where the CMB scales are, CMB constrains the primordial physics. Over these scales, the CMB is not sensitive to these scales, over smaller scales. So I can enhance power without affecting anything on the CMB scales. And if I enhance the power of the primordial perturbations, that is, I need excessive perturbations in density and pressure on much smaller scales, then what can happen is that they can end up forming these primordial black holes. Okay, I will skip this for want of time. Okay, you can have situations, where there is, on large scales, the power is consistent with the CMB. On small scales, there is excessive power, and they can end up forming these black holes. And I will try to explain this graph in a minute, okay, or by taking time for a minute. What has been plotted is the number of primordial black holes that contribute to what is known as the cold dark matter today. It's the fraction of cold dark matter today. In other words, if this FPBH is 1 somewhere here, over these scales, then what you essentially have is that all the cold dark matter in the universe is in the form of primordial black holes. What are primordial black holes? Primordial black holes are formed during the early universe, in particular during the radiation-dominated epoch, rather than the black holes that Arun would have talked about, which would have formed much later during the matter-dominated epoch, and they are essentially formed through astrophysical processes, while this is a cosmological process. It's not localized effect. It would have, primordial black holes would have formed all across the universe, not only at localized regions in space. So you can have, these are constraints on the, this quantity, on the number of primordial black holes that would have formed in the early universe, and you can have a situation where you can construct inflationary models. Some of them may be fine-tuned, some of them less fine-tuned, that can create as much as the total number of cold dark matter that is present in the universe. But what has this got to do with gravitational waves that we are trying to talk about today? Well, I'll skip these slides and go to this. Earlier, I talked about the primary gravitational waves generated during inflation. These are generated due to quantum fluctuations. And I made a very brief remark as to how, if you have anisotropic stress, they can also generate gravitational waves. It's a little technical, but I'm not able to escape introducing these technicalities to explain this part of the talk. So what essentially happens is that at higher orders in perturbation theory, scalar perturbations, dense perturbations in density and pressure can induce, essentially gravitational waves. These are known as secondary gravitational waves. In a similar manner, if you have magnetic fields present in the early universe, that is something else I could have talked about. I don't have time to fit that into. They can also generate gravitational waves. So there are many sources of gravitational waves in the early universe. There is one source of what is referred to as primary gravitational waves, which I have talked at a great extent. And if you detect these primary gravitational waves, you know much about the epoch of inflation. But there are other sources of primordial gravitational waves, that is gravitational waves generated in the early universe, and what this is, secondary gravitational waves. This arises because of the simple fact that you had this power, excess power on excess power on large scales, on small scales rather, and essentially because there are high scalar perturbations, they can in turn generate gravitational waves, okay? And this is the spectrum or the spectral energy density that I mentioned of these gravitational waves, secondary gravitational waves, okay? And they will have shapes like this. And by choosing certain models of inflation, I can ensure they occur during the, over a certain range of frequencies, for instance, which the pulsar timing arrays are sensitive to. So I'll just take a couple of more minutes and wind up, Chandra, okay? And this is the last part of the talk. You know about pulsar. These are rapidly spinning neutron stars with extremely precise time periods. And over the last 15 years or so, there have been efforts to correlate the arrival times of these pulsars from different pulsars. If there are gravitational waves generated due to various mechanisms, then what happens is that they will affect, the presence of these gravitational waves will affect the propagation of light from these pulsars, and therefore there will be deviations from the arrival times of these pulsars, which are otherwise remarkably periodic. And the question is, by measuring the arrival times or the deviations from the arrival times and correlating these arrival times across many pairs of pulsars in the sky, can I say anything about the background of gravitational waves that are influencing the propagation of light from these pulsars. The first point is as follows. When you try to determine this arrival time of these pulsars, it's called the timing residuals of these pulsars. And if, you can, when you correlate these timing residuals across different pulsars and average over multiple pulsars, what you can show is that, assuming they are affected by gravitational waves, you can show the following. These timing residuals correlated across different pulsars will have a specific pattern in the sky if the sources of gravitational waves are isotropic. If you have isotropic distribution of gravitational waves, then these timing residuals will depend on the separation angle between these pulsars in a particular fashion, and this is known as the Helling-Down curve. So the timing residual can be divided into two parts. One depends on this Helling-Down curve, and another which depends on the amplitude and the spectral index of these gravitational waves. Now, what could be different sources of stochastic gravitational waves? Well, any primordial source will be naturally isotropic and stochastic. But if you have, a remarkably uniform distribution of merging binary black holes, but if you are talking about black holes which have to emit in these frequencies, nanograph frequencies that the pulsar timing arrays are sensitive to, they have to be extremely supermassive black holes that I had mentioned in an earlier slide. So you can ask whether they could be due to a uniform distribution of supermassive black holes across the sky, or whether this could be due to other primordial source. Okay, and what one finds is that the supermassive black holes will point to a gamma or an index which lies somewhere here. Now you can ask whether some other primordial sources can fit better. I talked about how if you have excess scalar power on small scales, they will lead to secondary gravitational waves with a certain peak in the power spectrum. What one finds is that there are many sources of gravitational waves, but that were analyzed by the nanographs collaboration. One particular type of what is known as scalar-induced gravitational waves, okay, fit the data remarkably well with a much better Bayesian evidence than many of the other sources, including supermassive black hole binaries. We have carried out this analysis. For instance, if you have gravitational waves, the secondary gravitational wave generated during an epoch of reheating, this is the spectrum we obtain in a particular model, and these are the nanograph data with the error bars, and one of these blue curves, which is in either solid or dashed, fits the data remarkably well, and they are, they will have primordial spectra which have this form, and they are consistent with the constraints on, they will also produce primordial black holes, as I said. They are consistent with the constraints on primordial black holes, and importantly, such primordial gravitational waves, secondary gravitational waves, generated due to excess scalar powers on small scales, fit all the observations and fit the nanograph data with a substantially significant Bayesian evidence than the merging supermassive black hole binaries. In some sense, the PTA data possibly point to primordial gravitational waves generated through such mechanisms. Of course, the last word has not been said. There are many uncertainties, both in the data, in analysis as well as modeling. So you may hear more about it as we proceed. So I'm coming towards the very end of my talk. I'll close with a broad outlook. The increasingly precise observations of the CMB, okay, can be expected to help us improve, the current constraints on primordial correlations, and in particular, hopefully they will help us determine what is the tensor to scalar ratio and therefore the scale of inflation. As Arun would have emphasized, the observations by LIGO are a culmination of almost 50 years of effort to detect gravitational waves, and they have indeed opened up a completely new window to the universe. The observations by PTAs, which point to a stochastic gravitational wave background, offer a wonderful opportunity to constrain, the physics operating in the early universe, particularly the evolution of the universe, if it has a primordial origin. And of course, over the coming decades, various observatories, gravitational observatories such as LISA, Einstein Telescope, and Cosmic Explorer are expected to provide us with an unhindered view of the primordial universe. I talked about how gravitational waves carry information from very early stages of the universe. I should just mention that this talk, the latter technical part of the talk was based on these publications, and these are work done with a variety of collaborators and students. I really don't have time to emphasize their contributions. I'll just thank you for your attention. I'm sorry, Chandra, for having taken much longer than I had hoped to. Yeah.
Thank you, sir, for your wonderful talk. The floor is open for questions now. Anyone has any questions?
Since you mentioned that primordial black holes can range from the extreme lower mass to higher mass range, so let's say if we detect any black hole in the range of low mass gap, let's say 3 m0, so how can we rule out the primordial black hole from the, let's say, the stellar black hole?
Okay, I should be more careful in what I'm trying to say. What I said was that this distribution of masses came as a surprise to astrophysicists. They were expecting few, maybe 10 or 20 solar mass black holes. A range from 20 to about 200 comes as a surprise, and I'm sure Arun would have explained as to how, they are trying to find pathways to construct these black holes, and in turn help us understand the astrophysical nature of these black holes. It's a little more complicated if the black holes arise in this window, whether they are primordial in origin. They could be astrophysical, they could be primordial. But if you have something lying in this window like these guys, okay, where it is well known that you need at least minimum of 2 solar masses or beyond in order to form an astrophysical black hole. So if you have something of the order of 1 solar mass or less, I think you can be fairly certain it is a primordial origin. If it's higher, not all astrophysical processes have been understood to draw an exact line here about the threshold where it becomes a black hole. Am I correct, Arun? But if it is less than 1 or so, you can be fairly convinced that it is primordial in nature. Otherwise, it's a non-trivial task in confirming that it has a primordial origin. In fact, there is one candidate which has been in the news, I forget exactly which one, which has been in the news recently about it as that it is a primordial black hole. It could be a primordial black hole, but I haven't read those papers carefully enough to comment about it. But broadly, anywhere here and above, you need much more information to understand, to confirm that it is a primordial black hole. While here, you can, there are no other astrophysical mechanisms to indicate that objects with less than 1 solar masses could turn to a black hole. Where the line exactly lies is still uncertain. Am I correct, Arun? I think even these guys are still not sure whether they are neutron stars or black holes. So now it comes down, whether you like my model, etc. I can construct models where there is a finite probability for it to be a black hole. So, but I will be able to get only an FPBH which is 10 power minus 4 or 10 power minus 10. Are you happy with that? Okay. So, I mean, the FPBH I talked about is what fraction of cold dark matter in the universe is in the form of black holes. It doesn't talk about individual black holes. I can, get an FPBH of 10 power minus 3 at those masses, say, or 10 power minus 10, which means there is a finite probability, finite non-trivial probability for something to be, for a primordial black hole to have that mass. I can construct scenarios, inflationary scenarios, that will do that for you, okay? But the fact that it is, if it is less than this, you can be certain, okay, that it's primordial. Here, yes, it could be primordial, but you have to say that there are no astrophysical formation mechanisms for that to happen. I am not able to confidently say what are signals, pure signals of primordial black holes, other than the mass window itself. There have been efforts in this direction, but I am not on top of it. So on the gravitational lensing will induce B mode. Okay, so lensing of scalar perturbations can induce, exactly. Okay, so that's what this is. Okay, that's what this is. This is the primordial B mode. This is lensing, and that was also in here, right? No, this is instrumentation. This was lensing. Okay, so that is why I said you have to, before lensing becomes dominating, okay, you need to be able to detect. So if it is 0.04, there is, few multipole window for you to be able to detect. Okay, but what happens is that if R becomes smaller and smaller, as you can imagine, this will fall below the lensing contribution. We know the lensing contribution fairly well because we know the scalar amplitude fairly well. So if that is the case, if the threshold falls below this, then you are left with having to what is known as de-lens the effects, okay, to understand what is the primordial B mode on these scales. You need to remove the contribution to gravitational lensing.
So you need to have both E mode and B mode well measured.
Exactly.
And then a model of
exactly.
lensing model.
Exactly. And then you subtract. Okay. Is supposed to be primordial. Yeah. But it is significantly more challenging than being able to see direct imprints.
How do we know that the expansion of the universe itself was homogeneous? And do we have any idea about what's the shape of the universe in a broader spectrum? If the expansion itself is not homogeneous,
in a way that it's not homogeneous, then there might be some regions where you said that there are some anisotropies in the CMB model. It gives us idea about the temperature differences there. So how do we conclude that the space-time itself expanded homogeneously? Do we have any idea about that?
So what is said is that, because the anisotropies in the CMB are small, which means that the energy densities, so you are observing the anisotropies in different parts of the CMB sky. So let me maybe go to this particular slide to be able to explain this. So you are observing the anisotropies from different regions of the sky today. These anisotropies are essentially inhomogeneities on this constant time surface. That is deviations from homogeneity. They are 1 part in 10 power 5 at this time, and they are even smaller earlier. Therefore, there is no reason for us to imagine that the universe is, contain large inhomogeneities very early. And the fact that CMB itself is remarkably isotropic, it just implies there were no large anisotropies in the early universe. Okay? anisotropies in the universe means different rates of expansion at different points in different directions. Using general relativity, you can also show that unless you have source to drive these anisotropies will come down. Anisotropies and the expansion will quickly decay very early in the universe, number one. And there were inhomogeneities present in the universe, but they were remarkably small very early in the universe. Does that answer your questions?
So as we see the time evolution, the inhomogeneity decrease, like it.
The inhomogeneities grow with time. They were small in the early universe. Today, the universe is significantly more clumped than it was earlier. And the clumping arose because of the growth of the inhomogeneities. But during the early universe, the inhomogeneities were fairly small. I hope you understand. I can have also inhomogeneities in an anisotropic universe, which means anisotropic universe means the expansion of the universe is different in different directions. Using general relativity, you can show that the anisotropies in the background expansion will quickly decay away unless you have an anisotropic source. Okay, so and the CMB and other measurements tell you that the universe was remarkably isotropic. In fact, people are trying to see whether there is deviations from statistical isotropy, which will point out to say whether there is a special direction in the sky. And those also have been strongly constrained. Okay, there are some issues that need to be settled, and there are indications of deviation from statistical isotropy at 2 or 3 sigma, but they are not significant. So there are no reasons to, at this stage, to believe that the background universe was not isotropic.
Are there any further questions?
Sure.
So, suppose in the future when we have a B mode measurement about gravitational waves, you said that it put direct constraints on the energy density of inflation.
Because what happens is that the strength of the gravitational waves, since I know AS fairly well, and if I know R, I know what I refer to as AT. The strength of the gravitational waves is dependent only on the Hubble scale during inflation. But the strength of the scalar perturbations depends both on the Hubble scale and the inflationary model.
Yes, okay. So it's going to be extremely constraining in terms of understanding.
So that is why, that's why it's referred to as the Holy Grail. If I know the B mode, that's why I spent a lot of time on that part. If I know the B mode, I know the scale of inflation. And therefore, the energy scale at which all perturbations originated in the early universe.
Okay, I have some question about CMB Bharat, but I can come for the panel discussion.
Okay, sure. Yes.
Okay.
Sir, is primary and primordial gravitational waves different or the same? Like is it from
primordial means anything that happened in the early universe. Remember that window, that picture I had shown. Let me see whether I can go there. This is the picture I wanted. Okay. So anything that happened until in this time, okay, up to the time of CMB decoupling, there are various mechanisms, many of which I didn't talk about. Phase transitions in the early universe, merging of what are known as, topological defects, magnetic fields, they all can generate, or turbulence in the medium, all these can generate gravitational waves. Any gravitational waves generated in the early universe, in contrast to specific astrophysical sources that Arun talked about, I would refer to as primordial gravitational waves. Primary gravitational waves are generated during inflation. They are generated from the vacuum during inflation. And as I was explaining to Arun, if I know their strength, either through the CMB or something I wanted to emphasize with Arun as well, I hope I'm going in the right direction. Here, if I observe something here like this, okay, then and if it is, if I can if there are no other primordial sources, then I know the strength of the primary gravitational waves.
Also, sir, you were saying that the secondary gravitational waves can be it's because of magnetic fields. I mean, how do magnetic fields even give rise to gravitational waves?
So there are certain types of sources that can generate gravitational waves. Okay, so what mathematically you require, or so every matter field, or including gravitational wave, can be described by something known as the stress energy tensor. They correspond to the components of its energy density, momentum, pressure, stress, and so on. So if you have something known as anisotropic stress, that is, if I push in this direction, it will yield in a direction perpendicular to the direction of pushing. It's referred to as anisotropic stress. And if you have any sources which have anisotropic stress, neutrinos are supposed to have them. Freely propagating neutrinos possess anisotropic stress. They can generate gravitational waves. Magnetic fields are well known to possess anisotropic stress, and therefore they can generate gravitational waves. Much like certain currents and charges can produce electromagnetic certain motion of charges can produce electromagnetic waves. Okay, certain types of sources can produce gravitational waves. The only thing in this context is that you're not talking about isolated sources, you're talking about sources that are present in the entire universe. That's the primary difference between astrophysical sources and sources of primordial gravitational waves.
Thank you, sir.
Any last questions?
Sir, what if we consider it to be a multiple Big Bang happening at the same time? Will there be any changes in the gravitational waves?
So Big Bang is not a point in space, it's a point in time. It happened at all points in space at the same point in time. So I don't know what you refer to as multiple Big Bangs.
I was referring, sir, if we are considering the point of singularity from where the universe has started. So if the point of singularity was not only one point, if it was
one point in space or time? I just mentioned that it is a point in time, not a point in space. So firstly, that's a difficult question to answer about what the Big Bang does to gravitational waves. Gravitational waves, the manner in which I described, they are generated sometime after the Big Bang. They were generated about 10 power minus 35 seconds or after the Big Bang. Okay, I hope, there it is. Okay, they were generated much later. Around this time, 10 power minus 43 seconds or earlier, we refer to as a Big Bang by extending Einstein theory to that epoch. But we know Einstein theory will fail, around this time, around what is known as the Planck time, which is what that 10 power minus 43 second is concerned. So if you want, there is no theory, if you naively extend Einstein's general relativity, it points to a singularity. But physics abhors singularity. Singularities should not arise, which means the general theory of relativity has to be modified in order to describe the universe at these early times. So whether there was a Big Bang, it is clear there shouldn't have been a Big Bang. What replaces it is something we are not sure of. There are possibilities. You need a quantum theory of gravity, which people are working on, in order to be able to explain what replaces the Big Bang. So talking about multiple Big Bangs and so on, you will be able to say something about them, provided you are replacing this. Well, there are simple models without going into a quantum theory of gravity that replaces this part. There are something known as bouncing universes, where there was not a Big Bang at all. There was a contracting phase, and at some point of time, for some reason, the universe went into an expanding phase. In such situation, there is no singularity, there is no Big Bang. But there are other issues with such models, which I can explain to you in person later.
Okay, sir. Thank you, sir.
Okay, if you have any questions, we also have a panel discussion towards the end of the day. You can ask those questions then. And we'll break for lunch now. But I would like you to request just a step outside this building for a quick photograph. And then we can join for lunch in the same hall. If you haven't collected lunch coupon, you can just collect them right outside the hall where there's a registration desk. Thank you.